Good.
Wish you have a great time
Hello?
today.
From Iran, yeah?
Yes, I'm Iran now. I want to come there maybe next week.
Yeah.
On
And we're looking forward to see you. สวัสดีครับ อาจารย์ปิติ Hello, Professor Piti there. Yeah, we got there.
Hi, everybody. How are you?
Yeah. Yeah, I think it's a bit strange that we organize in this station, but I try to see everybody and say hello there. Professor Chayanon there as well. Okay. Right. Right. Well, now it's about time. So on the behalf of organizing committee, I would like to welcome you to the third International Symposium on the Construction Innovation Research and PhD Symposium, what we call ISCIR in 2022. We are the webinar hosted by Walailak University. Okay. So we have myself as the conference chair and also the co-chair, Professor Reyes from Warwick University, UK, and we have Dr. Montian as the conference secretary. This event is co-hosted by the Walailak University and Warwick University, and as well as the Chiang Mai University as well. It's also supported by the Thailand Council Fund and these two associations, Thai Structural Engineers Association and also Thailand Concrete Associations. So we have about 14 research partners and also with 3 professional associations and 2 industries. Yeah. So let me tell you in the past, the first ISCIR was organized in 2020 in Bangkok. So we have about 200 participants attend there. So I think it's at the first one, and I got one of my friends from UK visiting us in that time as well, and we got around 7 keynotes in that times. And after that, we moved to Walailak University at Nakorn Si Thammarat. So we have ISCIR 2019. As you can see there, and some of you already visiting us in that times. And I think we have a new friend from abroad as well. So they may wonder where we are. You can see there, this is Bangkok. And we are here, Nakorn Si Thammarat. So if you travel by plane, it takes about 1.5 hours by plane. And we also have the really tourist attract places such as the temples, Kanom beaches, Kiriwong village. So some of you might want to come visit over after the COVID get better. And it's about Walailak. So I hope in the near future, I hope to be welcome you to visit our university at Walailak. And last but not least, this is the friends, colleagues, professor, and supporting staff. I thank you. Without you, this event is not possible. So thank you. So I pass this event to co-chair, Dr. Reyes. Please welcome Dr. Reyes.
Thank you. Can you hear me?
Yeah. You can share your screen if you like.
Well, I don't have much to show really. I just wanted to mention briefly, just to thank you all for your welcoming words and for inviting me to present today and to chair different sessions. It's my privilege to be a partner in this conference. As Dr. Inject already mentioned, it's not the first time we organize this conference. This is actually the third of a series of conferences. We started collaborating with Dr. Inject many years ago. I won't tell you how many, but definitely more than 10. And we had the privilege to organize these two conferences before in Bangkok and then in Nakorn Si Thammarat. And we have carried on collaborating through different projects, shared project students, and papers, publications, and so on. So on behalf of all the organizing committee, all the chairs of the sessions, and the rest of the contributors to this conference, I welcome you all, and I wish you a very successful conference. Hopefully you will enjoy it, and you can take something with you back home. Thank you very much.
Okay, thank you, Reyes. So it's about the time now. Shall we start with the keynote one?
Yes.
You may give a bit of introduction.
Yeah. I have, is it 30 minutes? Yeah. Just let me time it because, right. Okay, so so the first presentation is entitled Recycling of All Tire Components in Concrete. That's given by Professor Kypros Pilakoutas. Professor Pilakoutas is a professor of construction innovation and director of the Center for Cement and Concrete at the University of Sheffield in the UK. And at the moment, he's a Royal Academy of Engineering Research Chair, which is one of the highest positions you can actually achieve in the UK. He obtained his degrees at Imperial College, London. He's also a visiting professor at the Cyprus University of Technology and the University of Science and Culture in Tehran, Iran. His research is in the fields of structural concrete, fiber reinforced polymers, fiber reinforced concrete, repair, construction innovation, and earthquake engineering. He has produced more than 500 papers and reports, mostly in referred journals and conferences, and he has led research contracts in excess of 20 million euros, including more than 20 European projects funded by the European Commission. And he has more than 30 patents awarded. Now, Professor Pilakoutas couldn't make it today, so I'm actually going to present on his behalf. So today, besides the Warwick hat, I'm also wearing the Sheffield University hat. So yeah, I'm going to try and share and present what he was supposed to present. This is not my presentation, I have to say. Can you see my screen now?
Not now.
Not now? Okay, just give me 1 second. Well, it says stop sharing. Okay, let me try again. So share my screen, entire screen. The system audio. Can you see my screen now?
No, not yet.
Yes.
Or do you want me to share for you?
Yeah, maybe, because I on my side, I get to the window. It says stop sharing. I can't see.
Okay, I can share for you.
Yeah.
Can you stop sharing first, please?
Yep.
Okay, here we go.
Yeah, so basically what I'm going to show you today is a brief overview of a large European project that we had the privilege to coordinate at the University of Sheffield. That was a few years back. And this project is called Anagenesi. That's the name you can see on the top left. Anagenesi means renaissance or rebirth. And you will see later on why, because we are basically trying to give new life to materials that otherwise would be discarded. I'm presenting this, as I said before, on behalf of Professor Pilakotas and also on behalf of Professor Maurizio Guadagnini, who was co-investigator, and on behalf of a series of universities and SMEs that you can see there at the bottom. Okay, next one, please. This is a brief outline of the presentation. Very briefly, I'm going to show you some of the work that we have done before at the University of Sheffield in terms of the use of waste materials in concrete. Then we're going to move on quickly to see why we want to reuse the materials coming from end-of-life tires in concrete. Then a bit of the project, and then we're going to focus on the technical and general aspects of the use of rubber in concrete, and then on the use of steel fibers and polymer fibers coming from the tires into concrete as well. And then towards the end, we're going to see some demonstration projects, design recommendations, and some of the exploitation that we achieved with this project. So the University of Sheffield, we have a relatively long experience of using waste materials in concrete. We started more than, when was that, probably 20 years ago, using waste glass, cement replacements, and recycled mineral aggregates in concrete. And then in the last 6-7 years, we have focused more on the use of wires coming from tires to strengthen and reinforce concrete. A very fair question would be, well, why do we want to use old tires and recycled materials coming from these tires into concrete? If we think about it, we can think of a tire as a structure, as a structural element. And as you can see with that table on the left, regardless of whether these tires are coming from cars or trucks or lorries, we have three basic components in that tire. First of all is rubber or elastomers. Basically, almost half of the tire is rubber. Then we have the carbon blacks, which are somehow mixed with the rest of the materials. And then we also have the metal wires that give the strength to the tire. And then we have some textile, which is essentially a polymer that we can use. And then a rest of components, chemicals, that are only a fraction of the total structure of the tire. And what we try to achieve with Anagenesi is basically use the rubber, the metal steel, the wires, and the textiles, the polymers in the tire to reinforce concrete. Next one, please. Next one, please. Yep. Another reason why we want to use tires in concrete is if we think about it, for every single participant in this conference, in this call, there is one tire wasted every year. So if you think about the number of people in the world, that's going to be a lot of tires. And then, by the way it looks, we're not going to run out of tires very soon, because essentially we produce millions of tires every year. On the other hand, if you think of the environmental pressures, at least in Europe, we cannot discard tires and just pile them up in landfills. We need to do something with those tires. And the way we many times use tires is sometimes to produce cement. So you think of the kiln. We send these tires to burn, produce energy, heat the kiln, but then we only get a fraction, less than 25% of the energy from those burned tires. So we are essentially wasting around 75% of the energy we had to use to produce those tires. We can only recover a fraction of that by burning them. So there is definitely some room for improvement there. This is a brief overview of the project. As I mentioned before, the name is Anagenesi. This was funded with the previous round of the European Commission fund. And basically what we try to do is to form a team of 13 partners around Europe. You can see there on the map on the bottom right. We had partners coming from different places, from Cyprus to the UK, Spain to Serbia and Croatia. And the total amount of this project was around 4.5 million euros, and it lasted 3.5 years. Next one, please. So these are the aims and objectives of the project. The main aim was to develop solutions to reuse all the byproducts coming from tires into concrete applications so that we can reduce the environmental impact. And we achieve this through different objectives. First of all, we try to produce highly deformable rubberized concrete and use recycled fibers for bridge and building applications, thinking also of base isolation systems. That's basically for vibration and seismic control. We also try to use the tires, the recycled steel fiber tires, to produce concrete mixes, to use on industrial flooring, precast elements, and sprayed concrete. I'm going to show you later on a couple of examples. Then we also try to use the polymer fibers, that's essentially the fluff you get from the tires, to produce concrete to control shrinkage. Shrinkage is an issue in concrete. Concrete cracks very easily. So by using the polymers, we managed to reduce shrinkage cracks, as we'll see later on. And then on top of that, we also wanted to deploy mini demonstration projects around different countries in Europe to show that we could actually use our solutions in practice. And then towards the end, we also developed design recommendations and life cycle assessment protocols to use these products safely and in the field. In a nutshell, this is the project flow chart. Going from left to right, you can see several circles there on the screen. But basically, there was a lot of work behind this project. I can't show you all the work in 30 minutes. So what I'm going to show you is just a light touch on the many things we did. We started by doing some waste material processing and post-processing to basically get the materials we needed into the concrete. Then we did extensive laboratory and material tests at different levels, going from the small scale to the relatively large scale. Then we did the large scale testing and monitoring, then the site demonstrations. And towards the end, we did CE marking in one of the products. And based on that, we also managed to produce some design guidelines. Next one, please. So let's see some of the main technical achievements. First of all, I'm going to refer to the rubberized concrete. In the case of rubberized concrete, we did extensive experiments. We tested more than 300 cylinders, initially in unconfined conditions. So essentially, we took concrete, we replaced part of the aggregates, both fine and coarse aggregate. We replaced that aggregate with rubber, trying to match more or less the same size of the aggregate, and then we tested those cylinders. And we went from zero replacement, that's the original concrete, up to 100% replacement of aggregate measured in volume. And then we examined fresh and hardened properties of those concretes. Next one, please. So in terms of the results for the unconfined concrete, if we refer to that plot on the bottom right, on the vertical axis, we have the strength of the concrete, that's FC. Towards the right, we have the actual strain, that's how much the concrete can deform. And keep in mind that that's essentially the value we use for design. At least in Europe, we use that 0.0035. That value is coming from that right side of that plot. And then on the left, that epsilon L, that's the lateral expansion of the concrete. Yeah, so we measured both the axial and lateral deformation of all the cylinders. And then you can see different curves with different colors. If you see on the right, you see 0% replacement up to 100% replacement of fine aggregates. And we can see essentially two things in this plot. If we refer to the axial strain, epsilon C, we see that as we increase the amount of rubber, we decrease not only the strength, the FC, but we also decrease the deformability of the concrete. Yeah, so the concrete fails at a lower level of axial strain. On the other hand, if we move now to the left, epsilon L, the lateral expansion, as we increase the amount of rubber, because rubber is incompressible, we expand much faster the concrete. And that's basically a trade-off. As we increase the amount of rubber, we essentially kill the strength and we produce a much faster expansion of the concrete. So what this is telling us is essentially there is no much benefit in just adding rubber by itself, because we're essentially killing the strength and reducing the actual capacity of the concrete. However, next one, please. If we can control that expansion somehow, we can use the properties of rubber to produce a more deformable concrete. And that's essentially what I'm showing on those two photographs. On the left, you can see what we did is confine that concrete, in this case using aramid fiber reinforced polymer sheets. So we wrap them, and later on we tested them under compression. I had a video here. Unfortunately, I cannot show it because that's essentially a PDF. The file was too big to show. But in those concretes confined with aramid FRP, we managed to achieve high deformability. And that's essentially what I'm showing now on this slide. Again, on the plots, I have in the vertical axis the confined concrete strength. Towards the right is the actual deformation of the cylinders. And then on the left is the lateral deformation of the concrete. And then this is for a 60% replacement of both fine and coarse aggregates. And what these results are telling us, if we look on the top right there, is that by using 3 or 4 layers of FRP, we managed to increase massively the actual deformation of the rubberized concrete to levels of 6 to 8%. And if you think about it, that's about 20 times the current epsilon CU, that 0.0035 I mentioned before, that we can use typically in design in different codes around the world. And of course, that has different potential applications, not only for seismic control, but also for control of vibrations or anywhere where you need deformability. This is another series of experiments that were performed at Imperial College in London. And this was done on medium and large scale columns. And these columns replicated bridge piers, and they were subject to cyclic loading, trying to replicate the seismic behavior. There are a series of parameters there. I won't go through all of them. These were essentially circular columns that we pushed and pulled. And what we did was basically compare columns with unconfined rubberized concrete and then columns with confined rubberized concrete, and to do a vis-a-vis comparison. So next one, please. So again, this was a video. This is basically a closer view of those two columns. On the left, that's the unconfined rubberized concrete, and then on the right, you have the confined rubberized concrete. Next one, please. So these are some of the results. At the center of the slide, you see essentially on the vertical axis, that's the load, a load applied on the two columns. And then on the horizontal axis, you have displacements. And then you can see there the two different lines, the loops. One is for the confined rubberized concrete, the other one is for the unconfined. And what these results are telling us is that the yield displacement for the two different columns was pretty much the same. However, the Aramid confined column had more energy dissipation, around 50% confined compared to the unconfined case. And not only that, the confined rubberized column also had more ductility, up to 25% for low levels of actual load, and up to 15% for those more practical levels of actual load. At Imperial, they also did some creep studies, and all I will say is that the creep behavior of confined rubberized concrete is not much different to that observed in conventional concrete. These results are coming from a series of shaking table tests we did at the University of Iași in Romania. And the main objective of these tests was to examine the behavior of confined rubberized concrete in shear. So what we did is we produced a scaled down building. It's half the scale of a natural building, only one floor. And we tried to fail this building at the top part of the columns. So you can see there the figure on the bottom left. We left some short columns because we wanted to produce failure there. The main idea was to produce large shear deformations in those areas. And then we cast these areas of the short columns with rubberized concrete. And you can see some photographs there on the right of the actual building and some of the simulations we did using Abacus. Again, this is just a view of the two buildings. On the left, what we have is a building with normal concrete. And on the right, what we have is a building with rubberized concrete confined with the same Aramid sheets. So let's see some of the results. Next one, please. So here I'm showing some of the initial results. On the left, I have the results for the conventional RC building. And on the right, I have the ones for the confined rubberized concrete. And then as we can see, the conventional building failed at a maximum acceleration of 1.6 G. On the other hand, the building with confined rubberized concrete survived that shaking. Even at 2G, that was the maximum we could apply with the shaking table, the building was still in good condition, and we didn't manage to actually break it. Now, if we compare the results at 1.6 G between these two buildings, this is what we got. For the normal concrete building, the short column had a drift of 11 millimeters, whereas for the building with confined rubberized concrete, that displacement, that drift, was almost 18 millimeters. So clearly, by adding the confined rubberized concrete, we increased the deformability of that building. And pretty much the same in thinking of the top floor accelerations. We managed to reduce the accelerations initially from 4G in the building with conventional concrete to around 2.2 G with in the building with confined rubberized concrete. That's a reduction of around 45%. Let's move on now to look at the use of steel fibers in concrete. And as I said before, the main idea is to use the recycled steel coming from the tires as a reinforcement in concrete structures so that we can improve their behavior. Next one, please. Yeah. Again, there is a lot of work behind this, because one of the main issues with the small fibers coming from tires, in this case, we're talking of very small fibers, probably around no more than 20 something mil. One of the issues is the classification of these fibers. There is a lot of work behind this. I won't give you all the details, but basically what we did in the project is we managed to identify the length and give a distribution of the fibers using optical methods. If you are interested, we can give you more details later on at some point. Okay, next one, please. There is a lot of extensive structural testing for these results I'm going to show you at different scales, going from the prisms that you can see there on the left to large slabs, and we're going to see some of those results in the following slides. So these are results coming from flexural tests on prisms. So you can imagine these are 50, 60 mil prisms by 150, if I remember correctly. And what we have in this plot on the vertical axis, we have essentially equivalent flexural stress. That's essentially the resistance of the element. And then on the horizontal axis, we have the midpoint vertical displacement of the prism. Yeah. And what we have is different curves. The first one, I think it's a black line on the very left. That's essentially a control specimen without any fibers. And then the other three lines, the colorful ones, these are concretes with steel fibers coming from tires at different levels of replacement, 10, 20, and 30. And what this is telling us, let's go back, please. Yeah, what this is telling us is basically as we increase the amount of steel fibers, we manage to increase the post-peak strength of the concrete. So you can see most of the concretes are failing at around 3, almost 4 megapascals. The importance of the fibers comes after that point, where we can see that as we increase the amount of fibers, the post-peak behavior improves with the amounts of fibers we add. And that's essentially what we want. Then after that, we also tried to see what would happen if we blended fibers. So that's basically the photograph you can see at the top. We have steel fibers coming from tires, those are TSF, plus industrial fibers. In this case, these are undulated fibers. So we mix them in different proportions, and we see the results there again on the vertical axis. That's the flexural strength, and then on the horizontal axis, we have the vertical displacements. Again, you can see a plain specimen there, and there is no post-peak strength. On the other hand, if we look at the different blends we did, at the very bottom, we have the curve only for industrial fibers. That those ones that set on 160, that's essentially only undulated fibers. And then on top of that, we have the blends, different combinations of steel fibers coming from tires and industrial fibers. And as you can see, the post-peak behavior is much better in the case of the blends. Why? Because essentially the small fibers help us to control the small cracking, yeah, when the micro cracking starts. But then once those cracks start to widen, the industrial fibers come into place, and they help us to control better the macro cracks in that particular case. So all in all, what this is telling us is that we get a better performance when we blend the steel fibers coming from tires and the manufactured fibers. These are some results coming from circular slabs. So these slabs were almost 2 meters in diameter, and they were tested basically under a point load. You can see there the setup in the photograph on the right. And again, looking at the results, what we have on the vertical axis is the bending stress. On the horizontal axis, we have central deflection measured at the bottom of the slab. And again, here I'm showing 2 results. The one at the bottom is again the results coming from a slab only with industrial fibers, the undulated fibers I showed you in the previous slide. And the other line, I think it's blue line, is a blend of tire fibers and industrial undulated fibers. And again, you can see the results of the this blending of fibers are much better than the ones without the blends. This is just a couple of photographs coming from those slabs in terms of the crack patterns. On the left is a slab with only undulated fibers. You can see actually a few cracks concentrated in particular regions of the bottom of that slab. And then on the right, we have a photograph of a slab with these blends of fibers coming from tires and the industrial ones. And as you can see on the right, we can actually observe more cracks, because basically there is a better distribution of cracks when we blend fibers. Next one, please. Yeah. Okay, moving on now to the use of polymer textiles in concrete. Again, there is a lot of background work and technology in this case, because one of the issues with these polymer fibers is that most of the times when you get them from the recycling plants, they are a bit dirty. They are mixed also with some of the rubber and some of the black carbon. So cleaning those fibers is one of the first things we had to do to be able to use them in concrete. And then for the cleaning, we had to actually produce a small machine that would help us clean the fibers so that we can take them later to our concrete. Again, I can't show you all the details of this. If you are interested, we can discuss it later on at some point. Next one, please. So this is basically directly results coming from shrinkage control. One of the things, as I said before, that we wanted to do is to control how fast the volume of the concrete changes, because that's basically what produces shrinkage. So the vertical axis, we have volume deformation in concrete, and then on the horizontal axis, we have essentially time. And we have different results there. The one at the very top is essentially the control specimen, that's plain concrete. And then we have a series of results. Some of them are for polypropylene fibers, those shown as PP fibers. They are typically used in many applications in civil engineering. And then you can see at the bottom, we have the results coming from the polymer fibers. And I think it's needless to say that the results we got from the polymer fibers were better than the ones coming from the polypropylene fibers. So that shows that the polymer fibers are effective at controlling shrinkage. Next one, please. I'm just looking at the time because it's already 30 minutes. So yeah, this is just a comparison of 2 concretes. The one on the left with polypropylene fibers, you can see early age cracking there, a few cracks distributed over the surface of that concrete sample. And then on the right, similar concrete, but now with polymer fibers coming from the tires. And I think it's evident the difference in cracks. The polymer fibers also helped us to control other interesting issues in concrete, like freezing, thawing resistance. Again, we have a series of results there. We have cumulative mass loss on the vertical axis. And then on the horizontal axis, we have different concretes with different applications. Clearly, the plain concrete is less resistant to freezing and thawing. If we add polymer, polypropylene fibers or the polymer fibers, the improvement is very significant. And you can see two photographs there at the bottom with the very good results we got also in terms of freezing and thawing when we use the polymer fibers into concrete. The polymer fibers also helped us to control spalling, which many times is an issue in tunneling, for instance. And here I'm showing a series of photographs. On the left, we have plain concrete that was subjected to a direct torch. We use a torch, and we basically fire at the concrete. And as you can see, the concrete spalled. And then we have some other photographs there with increasing amounts of polymer fibers. In the case of small amounts of polymer fibers, there was a bit of spalling in some of the cases, not in all of them. But as we increased the amount of polymer fibers, we didn't see any concrete spalling. So clearly the polymer fibers were helping us to control spalling. Next one, please. And then, as I mentioned at the beginning, we had a series of demonstration projects. I cannot show you all of them. These are just a few examples. This is a slab on grade that we cast in Croatia. It's basically essentially a warehouse. And again, the main idea of this was to use the products we were developing. So we did a blend of the steel fibers coming from the tires and manufactured fibers. And the total volume of this concrete was 240 cubic meters. So it was a relatively big casting we did. It was actually Bosnia-Herzegovina. Sorry, I said Croatia. Next one, please. Again, this is another demonstration we did in Spain. This was in northern Spain. I cannot show you the video, but basically what we did is, again, use the steel fibers coming from the tires to tunnel line a new section of a road in a motorway in northern Spain. Next one, please. And then we did also demonstration projects at a smaller scale, thinking, for instance, in railroad applications. For instance, the use of hybrid fiber precast concrete elements like sleepers, for instance, and other items there like screed repairs and slabs on grades. That's example I showed you before. Next one, please. And then there was also at the end of the project, there was some exploitation to do. Twincon Limited is essentially a spin-off company of the University of Sheffield, and it's the only supplier of high-quality reused tire steel fibers that can be used in concrete. Yeah, so one of the good things about this company is that it can essentially provide you a classified size of fibers so that it can be used in concrete. Next one, please. And these are some series of recommendations we did towards the end, basically for the different products we were trying to develop for high deformability elements using the confined rubberized concrete, also for manufacturing design, specification, and placement of recycled steel fiber reinforced concrete, which is probably the most mature technology we have at the moment. And then also recommendations for manufacturing design, specification, and placement of concrete with polymer fibers. Next one, please. And that's it. That's everything for me. Thank you very much. If you want some more information, you can either contact directly Professor Kypros Pilakoutas. His details are on the screen, or you can email me directly. I can give you some information as well, because I was quite involved in this project when I was in Sheffield. Thank you very much.
With a share on that. it's really nice video there, but we couldn't see it, you know.
Yeah, I know.
I would love to see it later on, especially the rail track, the one, the project that you completed already. We are working
it's a shame.
project, you know.
Yeah.
So any
I
question,
know.
please? I think we can have time for a few questions. Hello, David, you there? What time now there in Spain?
Hi, Tanusa. It's like 8:39, something like that.
Right.
Right. I have a question for Reyes.
Yes.
If I might.
Hi, David. Sure.
Oh, shit.
Any question, please?
Hola. Se ha perdido.
It's okay. We can hear you.
You can hear me?
Yes.
Reyes,
Yes.
good to see you. Long time no see.
Yeah.
The things like, what is the next challenge on using rubberized concrete? I mean, we know there's like this proof of concept that is working, but what are the challenges in really using this in the market, to put it in the market and get it used? Like,
Yeah.
you know what I mean?
Yeah, it's a very fair question. I can see at least 2 or 3 big challenges. One of them is obviously the intake by industry. Because obviously, at least in the UK, the brief is very strict, so it's not easy to make someone get a new product into the project, because otherwise they can be liable for it. So if I go and I tell them, look, I can actually make your elements better by using some rubber from tires in the concrete, I think they would be reluctant to do it, because essentially if something goes wrong in the long term, then they have to pay for the repair. So that's one of the things. Second one is obviously quality control and eventually CE marking, because we can produce lots of nice looking elements. You can even think of as an isolator, but obviously it needs to be you need to provide a scientific basis for the use in Europe. So CE marking would be another issue. And I think the other issue more on the technical side is also thinking of durability and long-term performance, because obviously we don't have results about it. There is also the other thing that we actually discussed this before. How much deformability is enough? Because we can produce very deformable concrete, but we still have to control drifts, because that's essentially what the codes ask us to do. So there is a trade-off there, and we need to try and keep a balance. We need enough deformability, but not too much, because otherwise people are going to feel uncomfortable. I mean, we both of us, we come from the earthquake engineering field, so you can't really let your building drift too much, because then people panic. So there are still quite a few challenges to go about it. That's at least my view. We can carry on talking for hours about this.
We talk about this a long time back in Sheffield, and I still have my Dutch, and I'm working on that too. But yeah.
Yeah, me too. Oh, so we need to have another meeting, because I have a student here as well working on that. But I think it's a niche application for very specific applications. I think it can work for some, but not all of them.
So we got another question, Dr. Montien.
Yes. Long
Hi,
time no see.
Yeah, good to see you too.
Yeah, I'm good. I have a question about, you need a large amount of rubber and recycled tire, and how do you get that in the large amount of that material to work on your project, on maybe you work on the larger scale? Can you get it from the market in the UK or in the EU?
Some of it, yes. In the case of the rubber, there are quite a few producers in the UK. And for this, most of the rubber we used in this specific project, we got it from Italy because we had an Italian partner who was providing the materials, the recycled rubber. The steel, we would get it from locally, and then Twincon, the spin-out company, would pass it on essentially for free, because they also, well, for free because they also get funding, these small companies. And then for the fluff, for the polymer fibers, again, we would probably get most of it from Twincon and some more from Croatia. So we actually had different providers for the different materials, but most of them were free for us, paid by money coming from the European Commission.
I got my student to ask you some questions, please.
Yeah, sure. Yep.
Can I go to study at Warwick?
If we can produce it at Warwick, was that the question?
She said she interested to start to work on this project at Warwick. She said it's possible for her to travel to UK and study in Warwick.
Yeah. I mean, I actually have a PhD student working on rubberized concrete. But yeah, you know, everyone is welcome to.
Okay. Any more questions?
If anyone is interested, just get in touch with me, yeah, beforehand, because we need to have a chat and see what interests you have and what interests I have, and find common ground.
Any more questions?
Yes, I have one more question because
Sure,
now
yeah.
I'm also working on steel fiber concrete, but it's just, you know, normal one, not the recycled one. Do you have any workability issue with your recycled tile? I mean, when you mix in the concrete, because the most issue, if you put, you know, more fiber, you have, you know, the problem of
Bonding.
workability.
Yeah, there is always a trade-off, because if you use too many fibers, it doesn't work, because you create more voids, and also you have issues with balling even when you are mixing. So you can see you're actually making the concrete worse. So as long as you mix in relatively small volumes of fibers, then it should be okay. What are you looking at specifically? Is it mainly the concrete technology or more structural behavior? I couldn't hear you, sorry.
I mean,
You're
for
muted.
structural application, what is the maximum percentage of the fiber that you can use? I mean, and it doesn't cause any workability problems.
Oh, I would say no more than probably 3. It depends on the fiber, on the length of the fiber as well.
Yeah.
But yeah, I think Dr. Inject is saying it time's up. But yeah, I would say no more than around 3 to 5%. You have to look at the fiber itself, because it depends also on the properties of the fiber.
Okay.
But don't put too much, because otherwise you
Okay,
kill the concrete.
Thank you.
That's all right.
Okay, thanks, Reyes. Okay.
That's okay. My pleasure.
You're gonna be the chair for next section, please.
Oh, really? Okay. Okay, who's next then? Professor Pitti, yeah?
I'm right here.
Are you there, Professor? Yes. Okay.
Yeah, I'm here. I'm
Thank
right
you.
here.
Okay, so the next presentation, and it's my pleasure to introduce Professor Pitti Sukontasakul
Thank you.
from King Mongtus University of Technology in North Bangkok, Thailand. Professor Pitti is a full professor in civil engineering materials and head of the Construction and Building Research Center at the Department of Civil Engineering at King Mongtus University of Technology. His research interests include bulletproof materials, rubberized concrete, phase change material, and more recently, his work has been moving towards the development of cement mortar for 3D printing applications.
Thank you.
Thank you, Professor Pitti.
Thank you. I'll
All
continue then.
yours. Yes,
Thank
please.
you.
Thank you.
Okay. It's already the end. Sorry. Okay. Here. You see my screen?
Yes.
Okay. Well, actually, today I'll present two research results, and because we've done some tests. So the first one is to get the optimum mix proportions of cement mortar for the 3D printing applications, and the second one is the use of microfibers and VMA, the viscosity modifier agent on the buildability of cement mortar. This is our first project related to the 3D printing materials, and we also built a 3D printing machine, a small scale one. We got this budget from the government, but very small budget, about $28,000 US. But anyway, all the results, my student involved, their names are in there. Kasidet, Dr. Bukit and Sila, and also Dr. Supachai. My present will have about 4 topics, introductions, and I present a little bit on the printing machine that we built in our lab, and then we'll present 2 of the test results and conclusions. Well, I mean, we know that construction industry is a labor-intensive industry. Thailand in 2016, we have 6.2% of the total workers are in construction. However, Thailand is also entered the aging society. So we say aging society. Last year, Thailand is in full aging society. We have 20% of people in senior citizens. In 5-6 years from now, I'll be one of them. So, and then so that's why we have a declining number of workforce. If you are in the university, you see that the number of students also declined significantly during the past 4 or 5 years. So it's not new to us. And in 2017, about 2% of the workforce have been decreased from 38 million to 37 million. So in construction, we know that we have used a lot of workforce, labor force, so we have to move towards automation. When we're talking about construction, we talk about the pre-construction, construction process, and something along the way, it's like design, management, something like that. So we look at 3 of them. We can see the 3 primary challenge on the automation. Something in the task during the constructions, like the robot that can lay bricks, machine that can paving load. We all see that on the YouTube. And then the other one is something like pre-constructions, like precast, the components of the house that's being built, and then put it in the real site. So that one is more likely in the 3D printing applications. So then the last one is design, planning, management, using of software, and something that enhance the productivity of the construction. So we have right now. I only see 3 things that obviously we can move toward the automation. And when we talking about 3D printing concrete or cement now, there are 2 things: the printer and concrete and material itself. The printer is like when you do in the old days, conventional 3D printing, the prints plastic, and the nozzles heat the plastic. the plastic come in solid form. You heat it, it melts, and then it's laid down. So as soon as the plastic left the nozzles and lay down, it turned back to it's solid, a little bit liquid, and then turn back to solid again. The property never changed. It never changed. It come back to the same property it used to be. But for cement, it's different. We have cement in the liquid form, fresh cement, fresh mortar, and then it's getting harder and harder and harder. The properties change all the time. The soil change and everything change. It gets harder and stronger. So we're dealing with two different printing machines that's completely different from each other. So the cement printers have to be able to print liquid cement mortar out in line shape, and then the material itself have to be able to stay in that line to withstand force or maintain shape, withstand force, the load that's coming up on next layer. So that's why when we talk to the 3D printing guy on the materials, I mean, not civil engineering material, but the material engineering, they're confused. So we need somebody who be able to make us the right machine. So when it comes to the materials, there are 4 things that we have to be able to do it. One is the flowability. The concrete has to be, the mortar has to be able to flow and has to be extruded. Like this one is not cement, but I took this photo because I want you to see that it has to be able to extrude like a toothpaste. And then it has to be able to build. So it has to be able to, it has to be strong enough in green stage, I mean in fresh stage, to be able to sustain load. And then it has to have time, appropriate time. The ability to print, not too fast, not too slow. And the open time is really subjective. It depends on you and you only. You decide you want 1 hour, 2 hours, 3 hours, 1.5 hours, 2 hours, 30 minutes, up to you. And then you have to mix decide that to make sure that it comes out the same way that you want. And for me, that the cement mortar for one particular printing machine, you could have many mixed proportions that have different open times, depend on how they do it in the design. So I would just give 2 pictures of my 3D printing machines because I don't want to talk too much about it because it was under the patent. We're doing patent with the government, the National Research Council of Thailand. So we have motor to drive, we have the containers, and motor to drive, and the head of the driving here, special design to push the motor into the hose coming out to the nozzles. We have steel frames to hold the nozzles to move in 2 directions. We have control unit. This is how it looks like after the end of the design. And we have software control. So we have CAD. We draw on CAD and then we put it on the CNC controller. And the CNC controller translates the CAD into the G code and then to the cam. The cam will control how the movement of the nozzle. I don't really know much about this, so yeah. And then the final specifications, we have 500 to 500 millimeters dimensions up to about 300 millimeters or 400, I forgot. The nozzle speed is 2000 millimeters per minute. The container is 4.5 liters, and we have speed. Nozzle diameter, we have 2 sizes right now. So the motor supply system is container. The reason I have to specify this because some machine continuous supply, but we don't have continuous supply. We do containers, so different. The budget is very low. We got budget from the government, 28,000. We spent 5,000 on this machine, so it's very effective though. And then we do the test So since we get the machine, now we need the cement that match our machine. So we select materials. We do some literature research to get the big proportion that we really like. And then we do some tests and flow tests. And then after that, we do flow tests, compression tests, printability tests. Then we set the criteria. So we can select one of the mid proportions that we really like it. And then we put on some microfibers and viscosity modifier, and then we test more. And then we test on layer deformation, which is another test from this test. So come out. So when we look through literatures, at the beginning I said 4, right? But then I thought it should be only 3. So the first one is flowability plus extrudability. So you can have cement that's flow, but not be able to extrude it. That we need to have both in our fresh cement mortar. So we need to have the one that flow and at the same time extrude into the line that we want. And then we want the one to be able to stack up in fresh at the time, because when the time it comes, when you go around and come back again, that stack, the first layer has to be able to support the second layer. So we need to have the right one that be able to support it at the right time. So then we need the open time, printability. The printability test is to get the open time. The open time is like the first time when you print cement, right? Fresh cement, it will very collapse. So it's like water. And then as the time passes, it will get like, if you print your head's like this, when you print, it go like this. And then as the time passes, it will narrow down into constant width that you want. It's constant width. As soon as it enters the constant width, uniform line, you call it open time. So it's a time that cement be able to print in a uniform line without any defect. And then after that, for a while, then it won't be able to print anymore. It will not uniform, or it will have defect. Then we call it close time. So the difference between the close time and the open time, we call it time gap. So that's something that we have to look also. But right now, we focus on the open time and close time. So I said open time is subjective because it's up to you. How do you want it? In my lab, I want it to be able to print within 60 minutes after the water touched the cement. So in your case, it could be 1.5 hours or 30 minutes, up to you, whatever you want. So, and then you decide to get to that. So we look at the materials in Thailand that we already have it, so we don't have to look fancy or high tech or anything. So we've got Portland cement. So Portland cement is, so we will talk based on these 3 topics. Portland cement is like strength, it's buildability. Fly aggregate is also strength, buildability. Fly ash, we have, okay, let's say 4 of these is admixtures, right? Mineral admixtures, chemical admixtures. We have fly ash that affect 4 of them, 3 of them. It's increased flow, and then the strength low because early strength low. Everybody in Thailand knows when you mix fly ash into cement, there is early strength drop, so buildability drop, and then the setting time increase. So that means the open time also increase. Silica foam, okay, everybody knows that silica foam increase strength, and then however it reduces the flow, it reduces time. So these 2 is opposite to each other. So we have to balance this. At the end, we just remove fly ash. We don't need fly ash at all. I don't think fly ash. Fly ash is useless for our case, but for your case could be different. So plastic sizes, super plastic sizes, increasing flow, also affect the open time because if you type T, in this case we use type T, so it's affect the flow and also open time. It's increased the open time too. Also the strength. Some superplastic sizes make the concrete compact better. So you have a little bit increase of the strength. So when you have, and then we have the water retaining agent. It's really important to have these things because as a cement passing through the hose, the water will lose. So we need something to retain the water along the way. So we decided to use a polyethylene glycol. We didn't use any commercial, we just buy polyethylene because I experienced this before, so I use it. I really familiar with polyethylene glycol. So I use it to make sure that the water stay in the mortar without being disturbed. So we come up with actually we have like 10, 20 of the mixed portion, but I only present here 7 of them. So I call it M0, it's the control. The cement, fire aggregate, and water, not the same. We need very low water cement ratio. And we have the silica foam 10%, fire 10%. And we have the PEG 2.5 of this plus this plus this. And then we have the 15% of the superplastic size, which we thought at the beginning should be enough to make it flow. So we have this as a control. And then we study the effect of the fire of the silica foam. Actually, we do more than this. We have 5, 10, 15, 20. So, but 5, 10 makes sense. So I put it here. Fly ash. And then we use this. And then we took the fly ash, reduce from 10 to 0, increase from 10 to 20. And then we use these two, M4 and M5, and we study the effect of R of the superplastic size. Because at the time, we already know that we have to come to these two, and then so we decided to work on the superplastic sizes, type T. So we do 3 tests. And we do the flow test. We do compression test at 7 days. I was confused, but anyway, my student, he chose 7 days. I would like to do it 1 day, so but 7 days is fine. So we do printing. We use let's show this picture then. We use glass, and then we draw 2 lines with 10 millimeters, and then we print it. And then as soon as it becomes continuous, and with the error less than 1 millimeter, we call, as soon as the time has arrived, then that is all our open time. And we measure three locations. We use the average value, 5, okay, let's say 5. And then as soon as it won't be able to print, the line disconnected, then we saw it close time, final time. So when we set up the criteria for the mortar too, we make sure that all the mortar flow within the thing that we want. So in normal conventional mortar, there should be between this 105 and 115%. So in our case, we said higher than 115%. And we got it from literature. So compressive strength also from literature. My students said 7 days larger than 38%, 28 MPa. So I said, okay, why don't you do 1? I said, do 7, okay. And then the open time is something that we discussed. So we want it like 60 minutes, and the time gap is 60 minutes. So we have after we mix water, we have 60 minutes before we start the first print, and then we have more than 60 minutes to push the whole thing out to the hose. So we have the flow. So we have M0, and then at M1 and M2 is the silica foam. When you reduce the silica foam, it's we got M1 and M2 is what? Sorry, silica foam. the flow increase, of course. Yeah, sorry. And then when we reduce the fly ash, the flow decrease. You increase the fly ash, the flow increase. And then this compared to this, this compared to this. When you reduce when I reduce the type T superplastic sizes, then the flow also decrease. But all of them is past 115%. So the strength also very good. We have strength that past 28 MPa. I won't go to the much detail. I got a lot of. And then the open time is well, since we have 2 of them that already passed our criteria, so we depend on the last one. We do many tests, but then I'll show you only 7 tests. And this one is the one that passed the M5. The M5 is the one that without the fire zeros and water releasing type T reduced from 15 to 10. Yeah. So we got very good open time, the one that we want, really want, less than 60 minutes. So we hang on to this one. So at the end, we conclude that one of this is good. And for plain mortar without any fibers or, but then we find that everybody in the world already knows about this. You know, it's not very significant or very, so we cannot publish our papers anywhere, and also we decided to move on to another phase. So we said, okay, how about if you put fibers and then VMA, and then we improve the buildability of the cement mortars on for 3D printing. So when we look at the buildability, set the ability of cement to resist deformation from cells to itself and from subsequent layers. Well, most of the 3D printing failures fail from the poor buildability. It got excessive deformations, and then it got geometry that trickles like this. It got crack like this. So it leads to when you have the geometry, when you have a flow that you cannot control, it go left to right. Geometry, you cannot control the geometry. The centroid of the columns of the structure is not balanced, so it leads to the collapse. So we think it's very important to have a cement that have very good buildability. So we said, okay, let's do this. So how do you measure this? You measure by first we have to determine, we have to find the theoretical height. Theoretical height is well, I mean, at the beginning, we don't really know how to find it, but then after that, we know how to find. And we just, at the beginning, we thought like, if we print the first line, and that's it. That's our first line is theoretical the height, but it's not the, I mean, if you can have theoretical height. I mean, if your nozzle is like, let's say if your nozzle is 20 millimeters, and then you print less than 20 millimeters, your theoretical height is based on your nozzle height. Okay, so if your nozzle height is 20, and you print at 10, your theoretical height is 10, because the nozzle will just squeeze through all the mortars, and then the height is controlled by the nozzles. But if your nozzle height is higher than the diameter, whatever drop in here is the first line, but it's not theoretical line yet. It needs to be determined later, but we won't get to that today, but later. So if we measure the total height based on the theoretical height that we already have, the ratio of the actual height over the theoretical height is the vertical strength. That's how commonly people do it all the time. But they also height and width ratio. Height and width ratio is height over the width. And remember when I said that when we start printing, the width is very large, the height very small. As we go on, the width becomes small and the height becomes larger. So the width and per height ratio is very small when the cement is freshly mixed, but as the time passes, the width and height ratio increase because the height remains constant. More height, you gain more height, but you reduce the width. So it's something that a certain constant of the also can be determined the deformations of the layer, particular layer, not the whole layer. Anyway. Yeah, why do we use fibers in VMA? Because the fiber is a solid component. So we want, and VMA is a liquid component. So when we add fiber into cement, we're dealing with something that we're dealing with the solid component. We increase solid component into the our fresh mortar. So it provides immediate support right away, reduce water, increase water requirement. But then the VMA, VMA is like, it's acting on the liquid part. It's like a polymer, you know, when you put VMA on, you pound it, you shear it, the polymer break. And as soon as you stop pushing it or break it or trying to destroy or shear it, then it forms the polymer network. It make your liquid sustain in a way that. So we would like to play on the liquid part with the VMA. When the mortar is pushed to the hose, it will shear along the way with the hose wall. So the polymer chain is broken all the way, and then it increased the flow, not the flow that we talk in the flow table that we're doing. That's nothing compared to the pressure that's going from the hose to make the cement flow to the hose. That's another shear level. And then after it come out, it remains stationed. And then the polymer chains rearrange itself. It stays better. So we're doing this. So big proportions look like this. We take the M5 and we name it M0, and then put VMA 0.1, 0.5, and then your fibers, microfiber. You can mix too much microfiber in your concrete. It doesn't work, right? So let's say 0.1. I used to ask my student to do 0.5, and just right now, I think I asked him to do 0.5. He gave up already. He said 0.2 is the maximum he can do. So okay, say 0.2. Volume fractions. So we do flow test. Open time test is a printability test, the one that we already explained. So we do buildability test. We print at 12 millimeters. Our nozzle head is 20 millimeters. So when we print at 12 millimeters, our theoretical height is 12 millimeters. So we have total layers, five layers, and we have print distance of the 200 millimeters, and we measure 3 of them. And then we do compressive strength test and flexural strength test based on the specimen that we print out. Okay. Remember when before that I was mentioned that we don't have enough time, so we're using the mathematical models now to do the open time, to determine the open time based on the test result that we have. So that will be our next step. So the flow, there's not much effect of the flow when we use the VMA, because the solid contents determine the rheology behavior of material with there's two theoretical that we can refer to. One of them is that let's say that rheological behavior materials of the granular suspension is dominated by granular phase. So if we don't disturb the cement particles, we don't disturb the sand particles, silica foam particles, then there shouldn't be any change or slightly change. So, and also the liquid, we do the shear flow table test, the shears really low. So that means the formation of the network is faster than the destruction of the polymer network. So the formation is faster than the disruption of the polymer network. So that means that's why it doesn't change. But then when we mix fiber, it's changed because we refer to this one because we are adding fiber that have a 6 millimeter length into that. So we're disturbing the solid part or granular part phase of the mortar. So the flow decrease. Also the water requirements also increase. Open time, yeah. If we do the open time, this result is not very good because we do it every 5 minutes. So it's like 35, 30, 20. But if you use a mathematical model, we will get 21, 30, 34. We will get something much better, the one that we looking for. Yeah. So when you do the VMA also reduce the open time because of the formation of the network, of the polymer network. And the fiber, of course, right? Fiber provide support right away. When you're talking about fiber, it's like when you print it out, fiber will align nicely, and then it will provide support to the fresh mortar. So also the water requirements make the mix a little bit drier, so it's able to form the shape that we want faster. So then we will look at the deformation. Then I think I all over the time. Okay, the M0s, the control mix, like you remember I said 12 millimeter is our initial height. So as soon as we print, it go down to 10. So we got 2 millimeter initial settlement, and then after we print another 2 layer on top, it go down another 1, and it remained there for like that. So it's constant at 9. So we have maximum settlement of 3 at 3 layers. As soon as you add 2 layers, total of 3, so it settles. And then when you look at the VMA, there's no initial settlement, it's like 12. But then as you add another layer, it's reduced 1. Add another layer, it's reduced another 1. As you add another layer, it's reduced in 0.5. So the maximum settlement of equal to 2.5. But this one is happen after you add another 3 layers, or total of 4 layers. So fiber is the best, is the one that we want to work with. And now we forget all about this. We move to fibers. So we have 12 millimeter, 12 millimeters, 12 millimeters. And then at another 3 layer add, we have 0.5 settlement, and then it stay the same. So we have maximum settlement of 0.5 after 3 layers of the total of 4 layers. So we said fibers is the best, followed by the BMA. Yeah. So we come to the mechanical properties, then we have the print that we come out, and then we flexural test. There the VMA and the microfiber also increase the flexural strength, but the compressive strength, yeah, I need to look at this. Right now, yeah, okay,
Prof.
sorry.
Yeah, we need to wrap it up, please.
Conclusions.
Yeah, thank you.
Yeah. So optimum mix proportion is this: no fly ash, 10% silica foam, and that's it. And then without the BMA, layer deformations, the microfiber is the best, followed by the VMA. And without the VMA and the microfiber, it's like maximum deformation is the most. It also have initial deformations. And we also have the printable time is decreased with the VMA and microfibers. And or the last one is not concerned. It's not. I didn't present this. We test. Okay. And I would like to acknowledge the funding from National Research Center, Cousins, and I would like to acknowledge funding from the yes, and Professor Bantier, Professor Prinya, Professor Suchat, Professor Vanchai, Dr. Subhachai, Dr. Thanongsak, the chairman, Dr. Picha, and all my students, Kasidet, Bushit, Sasarat, and Sila, and also thank you very much. Questions? Sorry, 5 minutes.
Thank
over.
you.
Thank you.
Thank you, Professor Pitti, for your nice
Yeah.
presentation.
I just stop sharing it.
Yeah, thank you. Do we have time for questions? Or shall we move on to the next presentation?
Yes, excuse me. Can you
Any
hear me?
questions?
Is there one quick
yeah.
question, probably?
Yes.
Please.
Sorry. Thank you, Professor. I'm Tosot from the Mahidol University. I have a question that how can you input the concrete into your machine, printing machine? And the second one is how can you inject your concrete through your nozzle?
Yeah. Okay. Thank you. We just pour it in the containers, but how we push it through the
Nozzle.
through nozzles, it's a secret.
Gravity force or the
No. We use mortar to push it, but
You have to pay for that.
Yes.
I think you filed a patent already, I think.
Yeah. It's a secret because we cannot share that.
Understood.
Oh,
Understood.
Professor may say that you got to pay to know that.
Yes.
Thank you very much,
Very,
Professor.
that's very difficult.
Yes.
Yeah, that's very difficult.
Thank you very much.
Okay. Thank you. I think we need to move on to the
Okay.
next presentation.
Thank you, Reyes.
Will be too late. Thank you, Professor.
Okay.
Nice to see you.
Mhm.
Okay, so let's move on to the next.
Reyes,
presentation.
before moving on to the next presentation, may I ask all of you to open the camera because we want to capture the screen for the information and put in the university website, if possible.
All the attendees, you mean?
Yeah.
Okay.
Please.
Yeah, don't be shy. And smile, of course.
We got a friend from Plymouth as well. You know, Reyes, Professor Bosson there. Okay, 1, 2, 3, cheers. Okay, here we go.
Did you fit everyone in a single shot?
Oh, we record the video and we're gonna put it in the website later on.
Because there are 53 people on the call and
yeah,
might be tricky to get everyone. Okay, shall we move on then?
Yeah, please.
Yes. Professor Pitti, there is one more question in the chat. Maybe if you have time, can you answer the question in the chat from Ilan about fiber dispersion, something like that. Okay.
I will type down.
Okay. Thank you.
Okay. Yeah. Thank you, Professor Pitti. Yeah. Thanks. I lost the thread because I can see quite a few messages there. Right. Okay. So let's move on to the next presentation, which is related to improved mechanical properties of cement stabilized pavements base using natural rubber latex, and that's going to be presented by Professor Suksun Korpi-Bulsuk. Are you there, Professor Suksun?
Yeah, I'm here.
Okay, good. Yeah. Thanks. He's from, excuse me if I get the name wrong, RIIE University of Technology in Thailand. Professor Suksun joined this university as a lecturer in 2002. His outstanding research, teaching, and service for the university, community, and profession over the years was recognized when he was appointed and promoted to the level of full professor in 2010. He's also an associate fellow of the Royal Society of Thailand, as well as a professor of the School of Civil Engineering and a founder director of the Center of Excellence in Innovation for Sustainable Infrastructure Development at the same university. He's also an academic Senate member for his university and also for Rajamangala University of Technology in Isan. He's presently the president of the International Geosynthetic Society, corresponding to the Thailand chapter, and he's also adjunct professor at Swinburne University of Technology in Australia. He also serves as an editor and reviewer for several national and international journals. He has extensive experience in publications, more than 500 technical publications in more than 313 leading journals. He has impressive numbers in his corpus, 58, more than 11,000 citations, and many more figures here that are quite impressive, Professor. Congratulations. And he's one of the interesting information here is he's in the world's top 200 scientists cited in 2021 by Stanford University. This is a list, a very prestigious list that was published recently. Professor Pilakotas was also among those 2%. So that's why I'm aware of this list. Thank you, Professor. The floor is yours. Thank you very much.
Thank you so much, Mr. Chairman. And you are very great that can read my name properly, because sometimes when I go to foreign country, many foreigners could not pronounce my name exactly, but you are very good. Thank you so much.
Thank you.
So
Thank you.
first of all, I would like to thank Dr. Thanongsak and his colleague who for making very wonderful seminar. I went through the topics of the lectures and found that it's very interesting, and also thankful for giving me an opportunity today to share with everybody today my keynote lecture. Let me first share my slides. Okay, my talk today is on the improved mechanical properties of cement stabilized pavement base using natural rubber latex, that later on I will call it as NRL. First, I would like to introduce all of you the three departments, that is the main three departments related to the road construction in Thailand. Department of Highways supervise approximately 50,000 kilometers of road in Thailand. Department of Rural Roads approximately 47,000 kilometers, and the Department of Local Administration that supervise more than 500,000 kilometers. In Thailand, we have pavement that can be classified into two groups, which is the paved and unpaved roads. But anyway, paved or unpaved roads must be constructed using the high quality materials that meet the requirement or meet the standards of the three departments. And nowadays, the high quality material is becoming lesser and lesser due to the high demand of the road construction for the country development. So one of the effective techniques, or one of the ground improvement technique that we widely use in Thailand is the chemical stabilization. And so far, the cement, Portland cement has been proven that it is very effective in terms of the engineering and economic point of view. This figure shows you that, let me change to the laser. This figure shows you the product, the hydration product that can link or that can bond the soil particle together. With the strong bonding, the strength increases with the increase in the cement content. And however, the stabilized material, especially with very high content of cement, and mixed with the material with sometimes very high fine content, normally occur the chinket crack at the early stage of the curing. With the repeated traffic load, the crack can be developed and finally results in the failure of the stabilized material in the tensile mode. That sometimes we call it as the fatigue cracking. And this figure shows you the development of the crack, that you can see that the crack start from the bottom and move up to the surface. And this is the large crack that we can see from the surface. And with this crack, it will create the so-called refractive cracks on the pavement surface that could be either concrete surface or the asphaltic surface. To overcome this problem, we have to improve the tensile ability. We have to improve the fractural ability of the stabilized material. Recently, one of the good techniques is to use the synthetic polymer together with the cement. And I show you the microstructure of the the cement stabilized material with the polymer additive. You can see that the after the polymer that normally in liquid form, after the evaporation, the film of the polymer would connect the soil particle or would connect the aggregate and enhance the tensile ability and hinge the fractural strength improvement. These are the results that I obtained from the literature, that you can see that it shows the relationship between the ITS, that is the indirect tensile strength, versus time, and FS, that is the fractural strength versus time. The last line is for the cement stabilized material, and the blue line and the blue line is for the cement polymer stabilized material. You can see that they both indirect tensile strength and the fractural strength increase with the with curing time, okay, and higher than those of the cement stabilized material itself. But for sure, everybody know that the synthetic polymer is not produced in Thailand, but we have to import from foreign country, and it's a bit expensive. To overcome this problem, the government of Thailand promoted the use of national rubber latex that later on I will call it as NRL. The NRL has the ability or has the property that very similar to the synthetic polymer that have very high tensile strength, elastic property, elongation, impact resistant, temperature resistant, and also the corrosion resistant. So why not use the NRL to replace the synthetic polymer that widely used nowadays? To make use of the NRL, we have to improve its property because of the protein surrounded the molecule of rubber would create so-called the particle flocculation. So normally we put the so-called the surface tan to improve. And I and my colleague have been funded from the Rubber Authority of Thailand to prove that the NRL can be used in low application in stress of the conventional synthetic polymer nowadays. So during the past 2 years, we have conducted a lot of tests on several soil. But today I would like to share with you some of our results on a particular soil, that is the lateritic soil normally used in the road construction. And the soil that test for presentation today is so-called the marginal lateritic soil, or somebody might call it as the substandard lateritic soil. That means the properties of the material could not meet the minimum requirement for base and subbase. As you can see that the CBR value is very, very low of approximately 10, whereas the requirement for base is 80 and 25 for base. And even for unpaved material, it requires more than 30. So to make use of this material, we have to improve it by cement stabilization. And the cement used in this research is just the OPC, or ordinary Portland cement. And the NRL used for this research is obtained from the Rubber Authority of Thailand, with having the rubber dye-rubber content of 30% and specific gravity of 0.96, pH of 8. And to confirm that, the as certain that the NRL could work very well with cement stabilized material and could be very, very benefit to the cement stabilization. We have to prove in the laboratory and also in the field. But today I show you the laboratory test that we have conducted in 2 ways. I mean 2 conditions. One in the static conditions, and the other is the cyclic condition to simulate the repeated loading from the traffic. And for the static testing, there are 3 types of tests that we have conduct. One is this UCS, that is the unconfined compression test, the FS, that is the fractional test, fractional strength test, and ITS, indirect tensile strength test. All the tests have been conducted following the ASTM standard, and the dimension of the samples is showing in the slides. The next is the cyclic tests. That 2 types of cyclic tests we have been conducted on the stabilized sample. One is so-called indirect tensile resident modulus, and this photo shows you how we conduct the test. And I call it as the ITMR, indirect tensile resident modulus. The test was follow ASTM D4123 standard, and the sample was subjected to a cyclic load of 30% of its indirect tensile strength. This loading frequency is 1 Hz with loading period of 0.1 second and less period of 0.9 second. The test was run up to 200 cycles, and the data from the last, I mean the data from the last 5 cycles would be taken to calculate the indirect tensile resident modulus following this equation. And the last test for the cyclic test is the indirect tensile fatigue life, or ITF test. The test was follow EN standard, and the size or the dimension of this specimen is the same as the one for the indirect tensile resident modulus. The test was very similar. The difference is only the stress level applied on the sample were 30%, 50%, and 70% of the ITS, I mean the indirect tensile strength. And the test was run until the sample completely failed. And this is the typical test result that I would plot in terms of the total horizontal deformation or some plastic horizontal deformation versus number of cycle. 3 zones would be obtained from the test. And the purpose of this test is to determine the so-called fatigue life. The fatigue life is just the number of cycle that the sample fail. So the longer or the higher the number of cycle means the longer the surface life of the material when we compare 2 or 3 try of the material. So from now on, I would like to show you the result of the static and the cyclic test. First, let's start with the Ucl test. These figures show you the stress strain curve under the Ucl test of the cement stabilized material and the cement NRL stabilized material. This 100 to 100 mean the cement stabilized material without NRL. You can see that with the increase or with the NRL inclusion, the stiffness of the material decreases, or we can say that the material ductile with the inclusion of the NRL. Not just only behavior that got improved from the brittle to the ductile, you can see the strength development. I showed you this is the plot between the UCS and the NRL replacement ratio. For the levels of cement, you can see that the strength increases to the max value, then decreases. The NRL replacement ratio at the maximum value is so-called or is designated as the optimum value. And this is the curve for 3%, 5%, and 6% cement. Interestingly, the optimum value is not fixed. It means, in other words, it changes with the cement content. The higher the cement content, the lower the optimum NRL replacement ratio. You can see that the development in strength is approximately 80% to 30%. Okay. Similar result can be seen from the FS, the fractional strength test, that you can see that the same behavior or the similar behavior can be obtained, that the maximum FS, the maximum SS is found at the optimum value. This is the result for the ITS, indirect tensile strength. From the three mechanical tests, we have found that the optimum NRL replacement ratio is the same. You can see that it is 20% for cement content of 3%, 15% for 5% cement content, and 10% for 7% content. Interestingly, without cement, without NRL, after the peak, you can see that this is the stress strain curve. Sorry, this is the load deformation of the cement stabilized without NRL. You can see that after the sample, after the load reached the peak value, suddenly the load dropped down to almost zero because of sudden failure of the sample. But with the NRL inclusion, the NRL film can bond the soil. And I in the reduce the sudden failure, that we can see the gentle reduction in the load after the peak value. This is another advantage of the NRL. So besides the mechanical property improved, I would like to show you the advantage of the NRL in terms of the earth saving. So this is the between the carbon footprint versus the NRL replacement ratio. So for sure that everybody can guess up to this point that I have two ways. If I would like to increase the strength of the material, let's say if I have initially the unconfined UCS of approximately 2.9 MPa, if I would like to increase the UCS of that material, there are two ways to do. Either increasing cement content or keeping the same content of cement, but adding the NRL. So I show you, this is the result that obtained from the lab, that if we wish to increase the UCS up to 3.5, up to 3.8, up to 4.01 megapascal, we have to increase the amount of cement from 3% to 3.8, 4.1, and 4.4%. For sure that when we increase the cement, more and more cement increase, more and more carbon footprint obtained. So instead of increasing cement content, I just keep the cement the same, but I include the NRL. You can see that the increase in the carbon footprint due to the increase of the NRL is much lower than that from the increasing cement content. And this is another advantage of the NRL inclusion or NRL replacement in terms of the world saving or in terms of the carbon footprint. So now I would like to explain to you how NRL improves the mechanical properties of the cement stabilized material by using SEM and XRD result. And this is the result of the SEM image of the cement stabilized material without NRL. And this is stabilized material with NRL, but at optimum content. And this photo, or sorry, this image are for the NRL over or beyond the optimum content. We can clearly see from the image that the film of the NRL would link the aggregates together and improve the confinement, also improve the aggregate cohesion, and that's why the mechanical property got improved. But once we add the NRL over the optimum value, what happened is the film would be very, very thick, and those thick film would prevent or would retard the hydration, hence the reduction in the cement bonding strength. So this is the XRD result to prove that with more and more NRL inclusion, the cementitious product would be reduced. So this is the XRD result of the NRL with treat and without treating. I mean the treat with the surface tent. You can see that the main element of the NRL is carbon. So from this XRD result of the cement NRL stabilized material, the C element increases, with the NRL content. Let's see, this is 20% and this is for 30%. Whereas the hydration product, that is the calcium silicate hydrate, Ca, Si, and Al, reduce. That is to confirm the retardant of the NIL film when we apply over the optimum value. So from now on, I would like to show you the another two results of the cyclic test with ITMR, indirect tensile resident modulus, and the fatigue life. So this figure show you the result of the ITMR versus NIL replacement ratio for 3% cement, 5% cement, and 7% cement. The same tendency of the result can be obtained that you can see that the result, this one is for 3% cement, and this is for 5%, and this is for 7%, that the same tendency is found that with the increase in the NIL replacement ratio, the ITMR increases up to the max value at the optimum value. Beyond that, the ITMR decreases, okay? And it is found that the optimum NIL replacement ratio and for the static response are the same. And due to that, we can plot the relationship between the ITMR and ITS, that is the indirect tensile resident modulus, because the result have shown that the optimum NIL is the same. So this is the plot that we have obtained, that is the red line. When we compare with the odd loss, you know, the odd loss is the standard of the Australia. And we compare with the odd load, and we compare with the result from the previous research, we can find that our result is among of the equation proposed by previous research. And the last one that I show you is the fatigue life of the cement NIL stabilized material, and also their deformation behavior. So first, I show you the advantage of the NIL in terms of improving the fatigue life. You can see that this point is defined as the fatigue life, and this is the result of the 3% cement stabilized material and 3% cement 20 NIL stabilized material. This curve is for the cement stabilized material without NIL. For the stress level of 70%, stress level of 70%, it means that the cyclic load that we obtain, that we apply to the sample is 70% of the ITS, the indirect tensile strength. That is a static ability. And this is the result for 30% stress level. You can see that the higher the stress level, the lower the number of cycle or at the failure. I mean the lower fatigue life. You can see that this one, for 30%, the fatigue life is much higher than the fatigue life of 70% stress level. Interestingly, when we include when we replace the cement with NIL approximately 20%, you can see that the fatigue life of the material increases approximately 2 times for 70% and less than 2 times for 30%. This is one of the advantage. So now I would like to show you the advantage in terms of rutting, resistance, or in terms of the permanent deformation resistance. You can see that this is the curve, this is the deformation, this is the horizontal deformation and number of cycle for the cement stabilized material without NIL. So the total deformation can be divided into elastic and plastic deformation. So this curve is for the elastic deformation, and this is for the plastic deformation. And the above figure is for the stress level of 30%. The below one is for 70% stress level. So let's see the result for the cement NIL stabilized material. You can see that the elastic behavior, the elastic deformation of the cement NIL stabilized material is higher than the cement stabilized material. That's why when you look at the result, you can see that the deformation of the cement NIL stabilized material is higher than the cement stabilized material at the same number of cycle and the stress level. But the most important is not that point. The most important is if you look at the plastic deformation, that is the key point for the pavement engineering design. You look at the plastic deformation, you can see that the plastic deformation of cement NIL stabilized material is lower than the plastic deformation of the cement stabilized material. Okay, that is this show that the lasting resistance of the cement NIL stabilized material would be better than the cement stabilized material. So
Professor,
I would like
Professor
to, yeah.
Professor, we need to wrap it up, please.
Okay, let me
Thank
wrap it up this one. No? So I showed you the result to confirm that the NIL inclusion can improve the plastic strength. That you can see that when we add it, the plastic strength would reduce and the fatigue life increases. Fatigue life increases. The red line is for the cement stabilized material, whereas the blue one here is for the cement NIL stabilized material. So also propose a dominant parameter that used for the so-called the mixed design, because we are geotechnical engineer and pavement engineer would like to make the job mix that's suitable for the loading condition. And the parameter that we propose is so-called the V over VSC, that you can see that it can fit the result very well, and also the fatigue life at different loading cycle and different the stress level and the NIL replacement ratio. So I would like to end up my talk with very simple two conclusion, with very two simple conclusion that the NIL is very useful and can be replaced of the synthetic polymer. The optimum NIL replacement ratio was found to be dependent upon the cement content. And at the optimum NIL replacement ratio, the cement NIL stabilized material has lower plastic deformation. That is very important for lighting design, and has higher fatigue life when compared to the cement stabilized material. And if anybody interested to my talk, you can detail with the publication that we have recently published last year in ASCE, 2 papers and 1 in the International Journal of Pavement Engineering. Thank you very much.
Thank you, Professor Suksum, for this very interesting presentation.
Thank you so much.
Yeah, thank you. I think we can move on unless there is a burning question, because we're already almost 15 minutes late.
Yeah, I've got.
Oh yeah, I'm sorry.
Relating topics. How can you mix the natural electric liquid in reality?
In reality, nowadays in NRL has been using nowadays in many projects in Thailand, and the mixing is very simple. That we replace it with the water. Let's say when we compact the soil, when we get the compaction test result, we will get the optimum water content.
Right.
Normally in the field, we compact the soil at optimum water content. So getting the value of the optimum water content, let's say 10%. we can, if we want to replace 20% of NIL, we just add, we calculate into the weight of the water, and then we replace the water with the NIL 20%.
Okay.
That is what we have done so far in the field.
Yeah.
Okay.
NIL nowadays have been using in many projects in Thailand, because last year the government of Thailand, promote this use of the NIL. So there are a lot of road construction in Thailand got this project that we call the one tambon, one load or something like that. Okay. Yeah.
Okay.
Okay. Thank you.
Okay. Thank you very much. So let's move on to the next presentation. The next presentation is entitled Mixed Design and Characteristics Evaluation of High Performance Concrete Using Particle Packing Model. And this presentation is going to be delivered by Professor Nakorn Si Thammarat. Are you there, Professor?
Hello, sir.
Yes.
Hello.
Can you hear me?
I'm Binay Karna. I'm research associate of Professor Nakorn Si Thammarat.
Okay. Are you stepping in on his behalf?
Yeah. Unfortunately, because of some health issues, he cannot join. So I'll be presenting on his behalf.
Okay, that's fine. That's fine. So you let me read quickly his bio, and then we move on.
Sure.
So Professor Nakorn Si Thammarat obtained his master and his PhD from the Massachusetts Institute of Technology, or MIT, which we all know. He's deputy director of the graduate school at Navaminda Kshatriya Dhiraj Royal Air Force Academy. He's also an adjunct faculty member at the Asian Institute of Technology since 1999. His main research is in the areas of pre-placed concrete aggregate, design and inspection of airfield pavements, development of repairing materials and special concrete, development of special mortars for commercial applications, and design and testing of protective structures for military purposes. He's been the president of the Thailand Concrete Association since 2018, and a couple of years ago, he received the Siam Cement Group Chair Professor Scholarship. So we have here also Binay Karna. He's presenting then on behalf of the professor. And we look forward to hearing from the research you have been doing.
Thank you, Dr. Rice. I'll be sharing my screen.
Yes, please.
Yeah, can you all see my screen?
Yes.
Yeah. So, first of all, hello and happy New Year 2022 to everyone. I'm Binay Karna, currently working as a research associate in Asian Institute of Technology, Thailand. And first of all, I'd like to apologize on behalf of Dr. Nakorn Si Thammarat, as because of some health issues, he couldn't join today. I'm going to present our one of our work on high performance concrete. This is a brief detail of our research work under Professor Nakorn Si Thammarat. So let me start with the topic. Like, our topic is mixed design and characteristic evaluation of high performance concrete using modified Anderson and Anderson particle packing model. So as we can see that with giant leaps in the construction industries these days, high performance concrete is widely used because of its high strength, high workability, high dimensional stability with good abrasion and chloride and impact resistance, high density, obviously high modulus of elasticity. So what is high performance concrete? High performance concrete, as ACI defines it, is a concrete that meets a special combination of performance and uniformity requirement that cannot always be achieved routinely using conventional constituents and normal mixing, placing, and curing practices. So some literature review regarding to the high performance concrete and CO2 emission scenario is like 4.6 billion ton of cement production was done in 2015 which accounted into 8% of the global CO2 emissions. So cement is contributing 50% of CO2 emissions from the concrete. So these are the some CO2 emission scenario related to cement and obviously related to high performance concrete. So what is happening is we need high performance concrete and we also need to minimize the use of cement. So ultimately to minimize the CO2 emissions in the environment. So for this, methods which are being used is partial replacement of cement with supplementary cementitious materials like fly ash, silica foam, stone powders, and they are also using hydraulic cement. And so, but is the partial replacement of cement only is not enough, as it decreases the desired performance of concrete mix. So how can we address this? This can be addressed by particle packing approach along with partial cement replacement. This can be a solution to this problem. So what is particle packing approach? It is a material gradation selected so that the small particles fill void created by large particles. And the void between smaller particles are filled by the even finer particles. So packing density is calculated, which is the ratio of volume of solid to volume, bulk volume. So in this method, what we do is like we take into account the gradation of each and every particle in the mix. For generally in the conventional mixes, what we do is we don't take into account the gradation of aggregates, sands. But in this method, what we do is we will take into account the gradation of sand, cement, each and every particle which are being used in the mix. So why particle packing approach is this approach is most scientific, as it considered particle size distribution rather than the empirical relationships and concrete performance related to the particle packing of its constituents, and different materials can be selected as cement replacements in this. So PPM leads to lower paste volume, lower cement requirements, and sustainable concrete development at lower cost for better performance can be achieved. So looking at the particle packing model, there is one modified Anderson and Anderson model. This is the formula for this, in which Q, the distribution coefficient, plays an important role, which is used less than 0.23 for self-consolidating concrete, around 0.3 for normal concrete, and we'll use it 0.35 for high performance concrete. So the objectives of this research work is to develop a mixed design for high performance concrete with low cement based on the modified Anderson and Anderson particle packing model using design of experiment approach, and we'll present 4 MPa CO2 emissions of the model and experimental mix in comparison to the reported value in literatures and IPCC guidelines. So for this, we have developed 6 control mixes using ACI 211.1 for comparing the outputs with 33 mixes from the PPM. Each mix design were tested for fresh property and hardened property, and durability studies were done for 28-day and 56-day testing to develop a conclusion. So first of all, what we did is we created control mix using ACI 211.1 for comparing with the PPM mixes. For this, what we did is we used water cement ratio to be 0.5%. and coarse aggregate to be 1088 kg per meter cube, fine aggregate to be 543, and high range water reducer, which is super plasticizer, to be 0.9% of the total binder content. So these are the material, these are generally the mixed designs of the ACI. The left one shows in kg per meter cube and the right one is in volumetric proportion. Where A, B, C, D, E are respectively cement, fine aggregate, coarse aggregate, silica film, and fly ash content. And later what we did is we used DOE for developing the mixed designs for the particle packing model, and we kept water cement ratio to be 0.5 and high super plasticizer, which is high range water reducer, to be 1.1%. And the distribution coefficient was taken 0.35 as we are concerned with high performance concrete. So these were the physical characteristics of the aggregates obtained from the lab testing, and these were the physical characteristics of binders obtained from the lab testing. As I already mentioned, we are testing the gradation, the properties of each and every particle in the mix. So the optimization of mix for UE was done for the PPM. The maximum coded level and minimum coded level for each of the 5 components were taken, and 33 mix designs based on the PPM approach was developed. So the left one you can see in kg per meter cube, and the right one you can see in volumetric proportion. So, and the mix design optimization was done using EMMA software. So I have just presented 3 or 4 samples and we did it for all the 33 mixes. And the results we got is like we compared ACI and PPM mixes. For slump, we get that fresh property of most of the PPM mixes were better than the ACI mixes. We were getting slump better than the ACI mixes. And coming to the compressive strength, for both 56-day, 28-day, and 56-day, for the same design parameters, the strength for PPM mixes were nearly 10 to 13% higher compared to ACI mixes. And talking about rapid chloride penetration test, which is a very important test for the durability, due to the better packing of the matrix, the PPM had better chloride permeability. And similar was the case with abrasion resistance test and absorption test when we tested for both 28-day and 56-day testing. And now coming to the sustainability analysis, which is very important in our research, the CO2 emissions per cubic meter for both, like for ACI and PPM, what we are comparing is ACI mixes has significantly more contribution in CO2 emissions compared to PPM mixes, as it is using more amount of cement. And for similar properties of concrete mixes, PPM showed 33 to 48% decrease in CO2 emissions compared to conventional ACI mixes. And CO2 emissions per MPa, when we compared like with the threshold CO2 emissions per MPa, the per MPa CO2 emissions for normal mixes, which is minimum of 9 kg per meter cube per MPa, decreased to 5.56 to 3.54 kg per meter cube per MPa with PPM mixes. And so the PPM presented lower consumption and CO2 emissions per MPa of compressive strength when compared to normal ACI mixes. So what conclusion we drew with our research is the particle packing model can be used for producing high performance concrete with binder content as low as 195 kg per meter cube. And for similar properties of the mixes, PPM showed 33 to 48% decrease in CO2 emissions compared to conventional ACI mixes, which is generally used, and lower cement, high performance concrete with partial replacement of cement by silica foam and fly ash can be designed using particle packing approach, which will contribute to use of waste material, while simultaneously it will decrease the carbon emissions. So for the possible applications of our research, we could use it to developing guidelines for more economical and ecological mixes, and high performance concrete could be designed at low cement with proper selection of ingredients. And we are also on the process of developing mathematical models for this. So thank you.
Thank you very much, Dr. Binay. A very interesting presentation and a proof that even small changes, even in the way we design concrete, can actually make a lot of difference in terms of CO2 emissions. And that has a huge impact because now the construction industry is pushing towards concretes without cement or with as little cement as possible.
Yeah,
I think we're still on. Sorry. Yes.
Yes, sir. Yes, sir. Our research, like this PPM method, is a method developed in very early days, like it was introduced in 1908. So it is not doing anything different. Just what we are doing is we are taking the properties, we are testing the property of each and every component in the mix. So we can just change the mix design a bit, and we are getting some outstanding results. So
yeah, absolutely. I mean, but it's knowledge that has been lost over the years. You know, we were carried away with tendencies and trends in design, and we just stuck to that for so many years that many of these things are well forgotten by now. I think we have time for a quick question. If anyone has any burning questions, and then we can probably break quickly for drinks, toilets, and whatever else we need. Is any burning question? Oh, everyone wants to have a drink.
You feel free to have some coffee break.
Yeah, okay. So I think we have a break now. Thank you again, Dr. Binay. Very nice presentation. Send our regards to Professor Sanakon.
For those
Hopefully
who have any question, you can also ask directly or just type in the chat box, then we can just read out.
Yeah. And again, if anyone has another question regarding any of the presentations we had in this session, I'm sure each of the presenters will echo on this. Just feel free to get in touch with us, and then we'll be happy to try and answer your questions or to help you with any sort of research you are doing at the moment. Yeah.
Yeah, I have just shared our contact. I've just shared my email address as well. If we have any questions regarding this, we will be happy to answer the questions.
Absolutely. Thank you very much. Thank you, Binay. So 5 minutes break. I think we're actually on time, Sanonsak. Because the next meeting is supposed to start at, oh, I just closed the file.
So we have 5-minute break, and
so it's only 5 minutes, yeah. So we'll be back at.
I think we
10:30.
We are on track. Yes, good time though.
Okay, okay. I think we're still on time. Yeah.
Okay.
All right. See you in a bit then. Let me.
Yeah.
I close my microphone and.
Vinay, will you stop sharing first, please?
Yeah, so I stopped.
Okay, we get back now. So the chairs of the next section will be Dr. Boksun from Plymouth University and Dr. Montian from Walailak University.
Thank you, Jantanoksak. And we have to reschedule a little bit because Professor Sayan could not make it today. So we have to move Professor Kim for the first presentation in our second section. So let me introduce Professor Kim first. Professor Boksun Kim is Associate Professor of Structural Engineering at the University of Plymouth. Professor Kim has obtained over £1 million in research grants from EU Horizon 2020, the Royal Academy of Engineering, the Academy of Medical Science, and the Institute of Structural Engineers since 2014. He has been working on projects involving steel and concrete structures, graphene oxide concrete, recycled aggregate in concrete, and plastic bottle house, which have led to over 40 research publications. As a fellow of Institution of Civil Engineer, a chartered structural engineer, the past chair of the ISCIR DAY1 and Cornwall engineering groups, and a member of the Engineering Professor Council. He has actively been promoting civil and structural engineer. So please welcome Professor Kim for her presentations.
Thank you very much, Chairman. There is some noise in the background.
Could you please mute the noise from Dr. David? Okay,
thank you. Yeah, thanks, Chairman. I'm Boksun Kim. I'm from Plymouth University. And I want to talk about my research in recycled aggregates in concrete construction at the University of Plymouth. We have 3 funded projects at the moment, so I'm going to explain one by one. And then I'm going to talk about a couple of case studies and in Southeast Asia, and then I want to mention upcoming events. Just briefly, I do research in cementitious materials with recycled aggregate, and currently we do some rapid chloride migration test as well as some strength tests. And I do research in cement mortar and concrete with graphene oxide. We have published a few papers on it, and yeah, concrete with plastics, especially PET flakes. And I also do research in steel structures, especially in cold form sections with holes in the web. One of my PhD students has just completed his viva. So we have 3 funded projects at Plymouth on recycled aggregate concrete. The first one, tailor-made recycled aggregate concrete, track for short, TRAC, is funded by EU Horizon. It's RIIE program, so that's the research, innovation, and staff exchanges. And that's a website if you are interested in, and it's a 4 years project. However, due to pandemic, we got another extension. So we have time until the end of next year. And we have 5 partners, including EOP. So EOP, University of Plymouth, is a coordinator led by my colleague, Dr. Shanshan Chung. And we have a European partner, Chalmers University of Technology in Sweden. And then we have 3 overseas partners, one in Thailand, PNRU in Thailand, and Tongdu Sang University in Vietnam, and Shenzhen University in China. So at EOP, we do durability-related research. For example, fire chloride migration and also fire performance test with recycled aggregate concrete. And the next project is a Royal Academy of Engineering project. In 2020, I was fortunate to be one of the 13 Frontiers Champion projects, 13 Frontiers Champions funded by the Royal Academy of Engineering to do this research in recycled aggregate concrete in Southeast Asia. So it's supposed to be a one-year project. However, due to COVID, we have a little bit extension. So we have time until the end of next month. And yes, as a Frontiers Champion, as a Frontiers Champion, I established a consortium for recycled aggregates in concrete in LinkedIn. So it's open for global research communities. If you're not a member, please join us. And we use this LinkedIn to advertise the event and also disseminate the outcome of the project. So last year, as a Frontier Champion, I hosted 10 webinars and then 1 online workshop and 1 in-person workshop. That happened last year, and then all the webinars were recorded, and the recordings are available on the project website along with the presentation files, thanks to the speaker's permission. So this is the webinars, the 10 webinars I hosted last year. You can see very famous researchers and experts in this area. And I'm going to show you the website briefly, because this would be a really good place to direct to your PhD students who want to do research in this area. So some information about the project and myself as a Frontiers Champion. And there is a video clip, and I'll come back to this later on. And here under our events, there are recordings and presentation files. And some stats about the webinars. About just under 1,000 people registered. However, the attendance was just under 500 from 42 countries. And this gave a really good message, and not everybody attends. They register and they want to attend, but at actual events, they may have other regions or busy meetings and so on. But the ratio was about half. So this gave a really good message to the academy and also other my colleagues. So how important the advertisement of the event. And the #1 country, the delegate came from the UK, not surprisingly, followed by India, Ireland, Malaysia, and Singapore. And at registration, about a quarter was female. And in terms of their job profiles, I was pleased to see that over half came from industry, practicing engineers, and then academics, about a quarter, and then students, about just over 16%. And we collected questions at registration from delegate and prior to each webinar, and then we passed those questions to the speakers so they can include those questions in their presentation. So the most popular question was about properties such as strength, stability, durability, and general performance, and followed by production, mixed design, and industrial use and policy. So a couple of case studies presented in our online workshop in July last year. This was presented by Mr. Quinn, director of Lego Tuan Cao JSC in Vietnam. So Vietnam loses 5% of GDP each year due to the non-efficient waste management. And Vietnam is one of the developing countries and very active in construction. That means they build a lot. Before they build, they produce lots of a lot of construction and demolition waste every year. So the most C&D waste is used to leveling riverbanks, as shown on the top left figure. And currently, recycled materials are about 30% cheaper than river sand for leveling. So there is some motivation there. And however, lack of space to store recycled materials. Okay, there is a regulation by the Vietnamese government. However, it's very limited, and the regulation does not allow for structural purposes to be used. So they can't use recycled aggregate for structural purposes at the moment. And another example is, this one is given by Mr. Nakorn Si Thammarat of CPAC Construction in Thailand. And he gave us a very good presentation, this case study, and how his company uses effectively and trying to use recycled materials as much as possible and trying to go to near zero waste. On the top left diagram, he divided into 3 areas. The blue one, phase 1 earthwork, and then phase 2 structures, and phase 3 and architecture and other purposes. And last month, despite Omicron, I was fortunate to grab this window of opportunity to fly to Bangkok and to host this wonderful workshop. That's the way I met Thanongsak. And I thank you for many Thai delegates who attended this workshop and participated and contributed to the breakout sessions. So in the breakout sessions, we had a few important discussions, and why, for example, barriers. So what are the barriers in the development of recycled aggregate concrete in Thailand? And the biggest barrier we found was lack of government policy, and followed by research and knowledge. Yes, we need more research in there. And then cost was another barrier. And then social acceptance and people and public awareness. And challenges, the biggest challenge we found the technology and methods, and followed by economy and friendliness, and also policy. And hence opportunities, big opportunities in technology, followed by eco-friendliness, and then industry effort and technology. So these are some challenges and opportunities we found. Lack of recycling plant and facilities, because it costs a lot of money to have the equipment and also the space they need to store. And whether a recycle plant is at the appropriate location, because construction happens in big cities and the recycle plants requires a lot of space, so they have to go to out of cities and far away from cities, and that will add another transportation, bring back to recycled materials and send back to recycled materials after processing. Yes, cost is a barrier. What we found was no or little policy or standard for the use of recycled aggregate, especially for structural purposes. And yes, quality control and classification is the most important one. So that was one of the barriers to stop commercializing the material. And then design strategy and code, adopted from existing and foreign standard. Because at the moment, many countries use just the ACI regular standard. And design for target strengths, we found that this is really important to go forward. Okay, one of the outcomes during this project, I have been invited to one of the task groups by FIV, International Federation of Concrete, task group 4.7 structural applications of recycled aggregate concrete, properties, modeling, and design. I'm about to contribute one section on chloride ingress, chloride migration and chloride ingress. And we are making, the task group is currently working on the bulletin, which will be published sometime next year. And another one, I hope this works. The Royal Academy of Engineering made a few videos on this net zero series, and the series 2 is about built environment, and they interviewed me about half an hour or so and gave me with a rows of questions, and I'm included in this video about 1 minute. So I
Kim
appeal
is a structural engineer and head of a project developing
of
reusing concrete from demolished buildings to build the next generation of homes and infrastructure. Dr. Boksun Kim is a structural engineer and head of a project developing and advocating for wider use of recycled concrete aggregate, especially in regions where construction is happening fast.
50% of the world's population lives in towns and cities, and this figure is expected to increase to 68% by 2050. Due to the increase of population and fast urbanization, in particular in Southeast Asia, cities need to provide more infrastructure, buildings and houses. However, as the space is limited, low-rise buildings are demolished and high-rise buildings are built in the same location. So this causes a problem, since the construction waste from the demolition is currently regarded as industry waste and unused.
It's a huge missed opportunity.
Generally, people believe that recycled aggregates give low strength and quality. Yes, quality control can be problematic, and also recycle companies require big investment in large infrastructure and processing machines. So currently, it's easy to dump things than recycle them. However, research has shown that quality can be controlled, and we can develop a target strength concrete using recycled aggregate. Policymakers should consider to promote the use of more recycled aggregates in construction.
And the next project is about GCRF networking grant funded by the Academy of Medical Sciences, and it's a networking grant, so it's capacity and capability building exercise. And the PNRU in Thailand is the PI, and my university is a UK applicant. It's a 1-year project, but again, due to COVID, it's likely to extend until next year. And we hosted a joint AMS and arranged international workshop in Thailand last month, and we'll be hosting more international workshops this year, both online and in-person workshops. This time is going to be Vietnam and or Malaysia. So if you are interested in attending this workshop and contributing this to the workshop, and please let me know. I think I am just 1 minute over. So thank you. I'm happy to answer any questions.
Thank you, Professor Kim, for information interesting, because I also have been working on RAC for a few years, and I think today I meet the right person, and maybe we can work more together about the RAC. I myself test several structural elements using recycled aggregate concrete, which I will be presenting at the end of this of today. And I think maybe we can share more information about recycled aggregate concrete and the potential of RAC in structural applications.
Yeah, sure. Yeah, sure. Please let me know. If you are interested in this area, and please email me and contact me, so we can discuss further collaboration, and then hopefully you can give a talk in my workshop.
Okay. I have one question about the future of RAC. in European country or in developed country? Because I heard that you have, maybe several projects that use the RAC in real construction. Could you comment about the use of RAC in developed country? I also heard China also use, a lot of RAC in industry.
I think the use of recycled aggregate is very popular at the moment. I know the research has been done for many years ago, and it has become more popular because of climate emergency and CO2 reduction, and also the circular economy, especially in European country and places like Italy and Holland. They are very, very keen. Yeah. In the UK, and also very keen due to circular economy. And I think I would say the future is bright. But my focus is going to be the practicality, not just the research, but we need to put it in practice. That is lacking at the moment. And to deal with that, especially in China and then Southeast Asia, policy. Policy, we need to really work on the policy, and some policies limiting up to 20%, up to 10%, and so on. But they have their own argument too. So we need to work with them and to tackle this barrier. But I would say future is bright.
Okay, thank you. Are there any questions from the audience?
Yeah, question.
Excuse.
How about UK? Is there any real projects or real structure that been using the RCAs at the moment?
Yes, we do. Yeah, we do, especially near us, near Plymouth. There is a company called Brunel Recycling Ltd, and they produce recycled aggregate, and they're using 100% recycled aggregate. They make Lego blocks. It's like huge blocks.
Okay.
About it looks like a Lego, real Lego. You stack together.
Yeah.
And they use them for retaining walls. Yeah, and it has been very popular. It's not, but main use at the moment is sublayer. Yeah, sublayer on the roads. That's very popular. I think that's popular for all other countries. But this country, they are making a real product like Lego blocks. And we are trying to work together and to produce more commercial blocks.
Bene,
Professor Thamma has questions. Okay.
I had one question, general concern.
Yeah, go ahead. Yes.
As we know that the quality of recycled aggregate, they depend on the loading and exposure conditions of the demolished structure. So how we check that each bunch of aggregate? My question is related to the practicality of this application of this. Like if the recycled aggregate is coming from a demolished structure, is it feasible to check each and every batch before using in any superstructure or any big structures? Like how do you control the quality of the recycled aggregate?
That is a very good question at the moment. There are several ways you can do, but what you are mentioning just now is, for example, real building, reinforced concrete building, and you are demolishing it. Yep. And how can you collect certain part, especially certain part may have good quality, certain part is a low quality. How can you distinguish them and then take it to the recycling plant and then process them? And that is, as I know, it was one of the projects happened at Delft University. And I had a chat with this researcher recently, and she explained to me very, very clearly. And they have invented some kind of equipment, and then just scanned the wall before demolition, and it tells you some properties like water cement ratio and strength and so on and so on. So you can advise the people, okay, this part is really good quality, can you separate from the others, and so on. Yeah. So that's the one thing. And the other one is while mixing, how will you control the quality of mixing with recycled aggregate? That is very, very key at the moment.
Thank you.
Thank you, Professor Kim.
Montian?
Yes.
If I can just say something quickly.
Okay.
Yeah, I mean, I think basically what we are talking about here is families of concrete. I mean, it's not one single recycled aggregate concrete. It's families, because concrete varies a lot around the world. So we basically need to end up, I think this is the right approach. We need to end up focusing on particular regions around the world to produce locally the recycled aggregate concretes. The other issue also is obviously the codes, because at the moment, if you go to Eurocode or to any codes, the equations you have there are mainly for normal concrete. So in a sense, we are also restricted in terms of the use of recycled aggregate concrete by the codes, and that's why codes also need to be changed rather than being prescriptive about what you have to design for, to be based on the performance of the elements of the concrete you are going to produce. So there are problems at different levels. Because as Professor Kim correctly said, I think the future is also very bright for recycled concrete. Thank you. Just wanted to.
Okay. Thank you.
Thank you.
Yes, I absolutely agree with you. And in the UK, we can't use recycled aggregate more than 20% for structural purposes.
Exactly.
And
yeah,
yes, we need to work with them. And not just to work with them, we have to get into BSI. Yeah?
Into their hearts.
Into BSI,
into their hearts,
the hearts
and the minds.
Yeah.
yeah. That's the thing. Because otherwise, it won't move forward. Thank you very much.
Yeah. Thank you.
Well done. Thank you.
Okay, thank you. I think it's about the time now. I think it's next presentation, please.
The next presentation will be from Professor Picha on utilization of bacteria for self-healing concrete. Dr. Picha Chongviwatsakul is currently an associate professor in Department of Civil Engineering, Faculty of Engineering at Walailak University. Her research area is construction material and strengthening of concrete structure. Okay.
Oh, thank you for the introduction, and good evening to ladies and gentlemen, and maybe good morning to the professor in UK. Okay, and the title of my presentation today is the utilization of bacteria for self-healing concrete. So maybe the topic is a little bit different from other professors. At the early age, the fresh concrete is prone to shrink when exposed to hot, dry, windy weather condition, and maybe the shrinkage crack is the most common cause of cracking in concrete structure. So recently there is a new type of the concrete, and we call the self-healing concrete, which is concrete that has ability to heal the cracks itself by adding some substance such as the bacteria to the concrete during mixing. And here is the picture of the shrinkage crack before and after the healing process. And the crack healing is due to the microbially induced carbonate precipitation or MICP process. And for MICP process, the urease producing bacteria has been widely used because of their high productivity of the calcium carbonate precipitation. And I will explain a little bit about the MICP process. So the urease generated by the bacteria can catalyze the hydrolysis of the urea as shown in this equation. And we will get the carbonate ions from this equation. And after that, the carbonate ions can react with the calcium ions from healing agent or the concrete itself to deposit the calcium carbonate for the crack filling. And the objective of this study is to investigate the self-healing performance of the concrete subjected to the shrinkage. And this slide shows the materials that used in this study. We use the Portland cement type 1 and river sand and the water for producing the mortar. And we also add spore forming bacteria obtained from Bacillus sphaericus LMG 22257. And this figure shows the microcapsule of the bacterial preparation. At first, we prepare our bacteria to be in the spore form. Then after that, we encapsulate it using the extrusion and freeze dye technique. We have to encapsulate the bacteria because we would like to prevent the bacteria to be damaged during the casting process. So here is the picture of the microcapsule after encapsulation process. You can see this is one of the microcapsule. The size of the microcapsule is about 1 millimeter. And we mix these microcapsule with the mortar or the concrete. So this picture or animation shows a little bit how it works. So first we make the spore of the bacteria and we encapsulate it in the microcapsule. After that, we put this microcapsule in the mortar, and when the crack happens, this microcapsule will be broken, and the bacteria will go out and do the MICP process. And this slide shows the mixed proportion we use in this study. We use the water to cement ratio of 0.6, the sand to cement ratio of 2.75, and we also add the spore forming bacteria at 0%, 0.5%, and 1% by weight of the cement. Also, we need to add the nutrients for the bacteria, which consists of the yeast extract, the urea, and the calcium nitrate tetrahydrate, which is the calcium source for MICP process. And this table shows the experimental cases. We have 4 mixtures. The first one is the control mix, which is just the plain mortar. We just use the cement, sand, and the water. No, we didn't add the spore nor the nutrient. For the second mix is S0. In S0, we add the nutrient, but we didn't add the spore. This mix, we would like to investigate the effect of the nutrient in the compressive strength and also the crack healing ratio. And the third specimen is S0.5, which we add the 0.5% of bacterial spore with the nutrients. And the last one is S1. We add 1% of bacterial spore with the nutrient. And because in the nutrient there are some water, so we need to reduce the amount of the water in our mix in order to control the total amount of water in the mix to fix the water to cement ratio. And here this slide shows the specimen preparation and the test setup. So we cast 2 types of the samples. The first one is the sample for the compression test. We cast the cube sample with the dimension of 50 by 50 by 50 millimeter to investigate or determine the compressive strength of the mortar. And the second type of the sample is the Inject specimen. Here is the picture of the Inject formwork. We cast our mortar into this specimen. Then after that, we put this specimen into the environmental chamber to control the wind speed and relative humidity. And after that, we will observe the Inject crack on the top surface of the specimen. And we need to do the water curing for MICP process. So we pour the water every day for 28 days. And also at the same time, every day we need to take a picture of our specimen to measure the crack width day by day. And here is the result of the test. The first, this slide shows the result of the compressive strength in the vertical axis. And here is the mixture in the horizontal axis. So you can see that the compressive strength of mortar decrease when the nutrient is added because the yeast extract in the nutrient leads to the formation of air bubbles in the materials. So the compressive strength decreased by approximately 50%. And the addition of the bacterial capsule increased the permeability, and thus the strength of the mixes decreased. And the effect was more pronounced for the specimen made with 1% of bacterial spore. And next, if we move to the crack healing efficiency, this figure shows the crack width of the specimen S0 mixture, which is the specimen added only the nutrient. Here is the picture of day 1, day 7, day 14, 21, and 28. And here is the crack width in the millimeter. So from this figure, we can see that the maximum crack width observed at day 1 was 0.79. Then after 28 days of healing, the maximum crack width that can be healed was just 0.28. As you can see here that this crack can be healed after 28 days. The specimen with only nutrient exhibit a crack healing due to the chemical reaction involving nutrients. And next, for specimen S 0.5, which is a specimen with 0.5% of bacterial spore and the nutrient. At day 1, we observe the maximum crack width of 0.82 near here. Then after the MICP process, we found that most of the crack can be healed at day 28. And the maximum crack width that can be healed was 0.74. As you can see here that it can be closed, the crack can be closed. But for the larger crack width, we still can observe the crack after 28 days. And next is the result of S1 mixture, which is the specimen with 1% of bacterial spore and the nutrient. So at the day 1, also we observed the maximum crack width of 0.8 millimeter. But just after 3 days, all of the shrinkage crack can be healed. So we can say that the shrinkage crack width of up to 0.8 millimeter was still after only 3 days of healing. And this figure plot the healing time with the crack healing area, which is calculated from this equation. We have 3 samples here, which are S0, S0.5, and S1. From this graph, we can see that the crack healing area increased rapidly during the first 7 days. However, there is a little gap in the percentage of crack healing beyond 7 days, okay, in this zone. And the percentage of crack healing increased significantly as 0.5% bacterial spore were added when we compare with S0 specimen. And the shrinkage crack formed in the S1 mixture was completely filled after 3 days, just after 3 days of healing. So this is the conclusion of my presentation. The addition of bacterial spore increased at the rate of crack healing in the early stage, which is first 7 days. And the second one, the highest healing efficiency of MICP was found in the mixture made with 1% of bacterial spore. And the shrinkage crack was completely closed after just 3 days of healing. And the last one, due to the negative effect caused by the microcapsule or the yeast extract in nutrients, the compressive strength of the specimen contained microcapsule and microencapsulated bacterial spore and nutrients decreased by up to 56%. And here is the acknowledgement. We would like to express our gratitude to our fund, which is from the Thailand Research Fund TRF and the Asahi Glass Foundation. And this is my research team and student. Okay, that's all my presentation. Thank you for your attention.
you, Professor Picha. So interesting, because today we learned about the bacteria, which is interesting. I have a couple of questions for you, Dr. Picha. How do you measure the crack width of your specimen? And the first one.
We take a picture and we use the computer software or program to extract the pixel in the picture and then calculate every day the change of the pixel.
Yeah, because the crack is very small, right? So you need special technique to measure the crack width.
Yeah, maybe, but not so special. Just take a picture, the same position, and put in the program.
Look like DAC, right? Digital image correlation, something like that.
Yeah.
Maybe that's too expensive. The second question is about the lifespan of the bacteria. Could you comment about the lifespan of the bacteria? Forever, or?
That's good question, but to tell you the truth, I have no result or no evidence on this point. I also heard that if the bacteria may have its lifetime, but in our project we make it into the spore form, and according to my knowledge, in the spore form the bacteria can live longer than the vegetative cell they call the live bacteria. So maybe, but I cannot tell exactly time that how can it still alive.
Okay, and it's not harmful, right? It's not harmful.
No.
Okay.
No.
Thank you. Are there any questions from the audience?
Yeah, I've got a question. It seems that you bring like something like alien to concrete or life to concrete, and remind me of zombie concrete, something like that. Yeah, say back to Dr. Montian's question, is it harmful to human by breathing, or even dog come to lick it over there, something like that?
According to my knowledge that I talked with the professor in Department of Environmental Engineering, she said that this is not harmful bacteria, this person.
Have you tried yourself?
No.
You can use one of your students. You have many students. Ask one of your students to try it.
Yeah, maybe I try. I will let you know later.
No, we're joking, of course. Actually, can I ask you something quickly, please?
Yes.
I think my main concern is actually the huge drop in strength.
Strength, yes.
Yeah, because I mean, if you reduce the strength of the concrete by 50%, you will probably need to use more cement. So have you thought of any way to compensate for the loss of compressive strength?
Yes.
I know some applications it may work because you're already at around 20 megapascals. So if it's a non-structural application, maybe you can get away with it with 20 something megapascals. But obviously, if you are thinking of more of a structural element that experiences shrinkage, like a slab, for instance, a slab on ground, then you probably need a higher strength. Have you thought of any potential solutions to compensate for the loss of strength?
Yeah, very good question. So I will answer you like this. So actually, you already answered your question. So after we saw this result, we recommend, actually we have a previous result just like this. So we recommend the use of the MICP process for the non-structural element. So it should not be the load carrying element, something like that. And if we would like to use in the structural element, so we need to compensate by use more cement, just like your suggestion. But recently in the research topic, we try to use less amount of the yeast extract and try to reduce the size of microcapsule. So we hope that by using less amount of yeast extract and smaller microcapsule, maybe the strength will not drop this much.
Drop so much. Okay. All right.
Yes.
That's fine. Thank you.
I think Dr. Montian or Dr. Boxon can put this in the recycled concrete somehow.
Yes, that is a
I'm
good
also
idea.
thinking about, adding fiber in this. Fiber and bacteria, you can reduce the bacteria and you can,
Or even
increase
put
the
some
practice with the
confinement from
fiber,
this.
something like that. Yeah.
Oh, thank you.
FRP. FRP.
Yeah.
Well, in our research team, we have discussed that already. yeah, good idea.
Yeah.
Thank you.
Okay, I think it's about time now for next presentation.
Thank you very much.
So I think it's my turn to introduce the speaker.
Yes,
And,
Professor Kim.
Next talk is by Dr. Thosawat Walailak. I hope I pronounce his name correctly. He is a lecturer at the Department of Civil and Environmental Engineering at Ucl University in Thailand. He obtained a PhD degree in Civil and Environmental Engineering from Hiroshima University in Japan. His PhD degree was fully supported by a scholarship from the Ministry of Education, Culture, Sport, Science and Technology of Japan. His bachelor degree is in civil engineering was from Ucl University, and his master degree was from Chulalongkorn University in Bangkok, Thailand. Dr. Walailak, the screen is yours.
Thank you very much, Professor. I hope that I'm showing my presentation screen, right? Okay.
Could you have presentation mode, please?
I see.
I think you
The wrong
need
screen?
to select the wrong screen. Yes.
Okay, got
So
it.
you need to go to the screen show and select the right monitor.
You need to swap.
Yeah, right. Yeah.
Okay, thank you very much.
Thank you.
Okay. Good morning and good evening, everyone. Today is my pleasure to share my experiment that is a part of my research is uniaxial load testing of large-scale 3D printing concrete wall and finite element model analysis. Okay, I really quite believe that you have heard about 3D printing, one at least. The implementation of three-dimensional printing introduced many new possibilities for the production of the concrete structure. One of them is a less formwork for construction, which could reduce a lot of construction costs and amount of labor required. So 3D printing concrete allows you to print where you design, and the architectural work is also flexible to design. As you can see in the figure 1, that is a dome house from the freeform printing. And figure 2 is a project milestone from the Eindhoven University, Netherlands. There are two types of the printing processing technology for the 3D printing concrete. One of the most popular is extrusion-based. It is a field deposition modeling, in which concrete material is deposited layer by layer. Using an extrusion print head is called a nozzle that you can see in the figure, the yellow one and the silver one. And although 3D printing concrete technology has been developed for 2 decades ago, the case studies are being presented on a regular basis to showcase the potential of the digital fabrication concrete. It is just only a few studies have been performed on the capability of the printed large-scale concrete structure element, especially is what considered of the architectural freedom design work that can affect the performance of the structure. So the objective of my present study was to analyze the capability of the large-scale 3D print concrete. The figure 4 reviews you the concrete printing freeform wall. You can see this one is uniformless. And this present study, the experiment is on the assumption that the wall is being load-bearing wall. So the compressive strength test was used to evaluate the capability of the wall as a structural element. As you can see in the figure, my experiments consist of 3 parts. The first one is the top beam, the second one is the bottom beam, and the third one is the wall. The bow of the beam is what created in order to support the loading. And the table 1 shows you the mechanical property of the concrete beam material. The working time is about 60 minutes. Setting time is 90 minutes. The compressive strength in the cubic size is about 50 to 60 megapascal, and tensile strength is about 5 megapascal, and the density is 2,200 kilogram per cubic meter. Why we need such a property? Because it can create a rheological property and soft solid. It is important character for the fresh concrete. Furthermore, they have long enough setting time for printing and depositing concrete layer by layer without a cold joint. In this study, 2 types of wall were printed in the large scale with the hypothesis that 3D print concrete can be printed in a complex geometry. The double layer wall, as you can see in the cross section with the inner truss, this one we call is a flat wall. And the next one, they have the webbing surface, and the backside is a flat surface. This one we call the diamond wall. The lovely dimension of the bow is 130 centimeter width, 10 centimeter depth, and 80 centimeter height. Anyway, the depth at the pit of the diamond wall is just only 6 centimeter and 12.5 centimeter at the pit. For the monitoring, strain gauge and RVDT were attached at each wall. To the position and the direction of the sensor are shown in the figure. The wall specimen were placed into the compressive strain test machine, conduct under loading at about 4.5 tons per minute. The maximum loading for the bow is approximately 110 tons. In the case of the diamond wall, the first crack of the diamond wall specimen was observed at a load of 36 tons that appear at the position between the peak and the pit in the red circle here. And at 90 tons, cracking between print layer could be observed, and the crack on the other side appear here. And finally, at 110 tons, the wall lost load bearing capacity to existing cracking, spalling, and explosion. It's completely decomposed here. Meanwhile, for the flat wall specimen, the first crack was observed at 25 tons. That is a little bit lower than the diamond wall, and the vertical cracking from top to bottom were appearing in the range 60 to 110 tons. But the big difference between flat wall and the diamond wall specimen is that the flat wall have no explosion and spalling breaking away from the surface. Although the loading test of flat wall was stopped at 110 tons due to the safety concern, but by the visual inspection, the wall could be bearing load larger than that because it's still good here. As you can see in the figure 12 is the result of the displacement in the lateral axis. I apologize that I did not show you the result of the strain gauge, but for the displacement, the lateral axis in the red line of the diamond wall here. It shows that the displacement is larger than that of the flat wall about 3 times. And furthermore, the extreme height of the tensile strength could be found on the surface. So we could conclude that the diamond wall was collapsed by bucking and tensile force. But for the flat wall is the cracking occurred by the tensile force. For the study of the model analysis, the flat wall specimen was created as a 3D model using software and analysis by finite element as seen in the figure 13. Finite element analysis indicate that the cracking began at the surface layer instead of interlayer bonding. So the result also indicate that the cracking on the wall surface was induced by the tensile stress, which correspond to the high strain of the experiment result. And after that, we want to know the behavior of the inner truss. We eliminate the inner truss in the 3D model. I found that the inner truss play a significant role in the bracing between the double layer wall, which could prevent the wall from the backing failure. In addition, the inner truss also improve the bearing load capacity of the wall. And finally, from the experiment, we can conclude it into the 5 points. The first one, although the 3D print concrete technology allows a flexible architectural design for wall structure, but the pattern and the layout of the wall surface affect the performance of the structural element. And the second one, the study indicates that the inner truss inside the 3D print concrete plays a role in the wall bracing. And the third, the strain gauge measurement result indicate that the different types of the strain can occur in the same direction on the same wall surface. The second last, a wall without the inner truss has a higher risk of the backing than the wall with an inner truss. And the last one, the mechanical property of the 3D print concrete wall are affected by the complexity of the wall design. Thank you for your kind attention.
Okay, thank you very much, Dr. Thosawat, for your wonderful talk. We now invite questions. I've got one quick question for you. You made looks like an I-beam. Yep, the shape I. Yep, it looks like I-beam. I understand the dimensions are less than a meter. The depth is less than a meter. Where do you see applications? There are no reinforcement inside, are they? It's just purely concrete. Yep.
Yes.
Where do you see applications?
This one can use as I said earlier, I assume this one is a load bearing wall, so we can use it without the steel bar. Anyway, at this time, this assumption, this synthesis can use just only for the 1 story of the building. For the second story, we are research for the new construction to use the 3D print without the steel bar, or in the worst case, if we need to add the steel bar, we have to use some kind of smart method. But now it's under researching.
Mm-hmm. Okay, yeah, thank you. So you want to use for example, building construction, yeah, without reinforcement, yeah, 100% just concrete. Right, yes. Okay, thank you. I think we had one question from Dr. Garcia. Do you want to? Sorry, I thought you raised a hand. Or...
No, sorry. I was actually. I was trying to clap. Sorry.
All right. Okay. So you.
Thank you very much.
Thank you.
Hopefully, I got it right this time.
So any other question from the floor?
Calculation.
Yes.
I had
sure.
one.
Yeah.
Yeah, I think if I understand correctly, you did 2 specimens, flat wall and diamond wall. And I'm not really sure how you work out on the ANSYS modelings. You know that when you use the 3D printing, you really cannot control the exact geometry. When I zoom it, I'm not really sure how you control it perfectly like this. In reality, it's really difficult to control. And also the material model, that is the crucial point to get the right result.
Okay, firstly, the exactly dimension of the specimen. Our printing machine is a high accuracy, so we can rely on the accurate the dimension of the specimen. And the second one, to model the 3D model in the ANSYS. I use the model based on the model for printing. Before we print the wall, we have to create a 3D model in the software first, And after that, we use a slicing, and then we put it into the printing machine. I use that, the 3D model before printing, import into the ANSYS, and then we use it to analyze.
Have you tested any materials or component tests to see the stress strain curve and input that in the model?
Not yet, but at this moment, we are a lot of topic we have to do. One of them that I will review in soon is the effect of fire accident, high temperature, under high temperature. High temperature, I mean, is over than 1000 degrees C, that I will review in soon. But for the basics like carbonation test, how should I say? The misproportion, I cannot show in this.
No, I mean, what I mean is, if you get the right material quantitative model,
yes,
you just model like a cylinder or cube, and just try to using model like CDP or something like that.
Yes.
Once you get the right model, right prediction, then you can extend to the last structure, even or the whole house. And in fact, it's not really the load acting vertically. You got to combine load.
Yes.
Laterally as well. It's load bearing wall, right?
Yes.
Yeah, and also the geometry. In reality, what I have seen in Salaburi province by SCG there, they built a house like in your second slide. So it curved shape like that. That will affect the load distribution as well. But interesting though.
Yes, it has same result because it's what is cooperating with the private company that's SCG.
Yeah.
Right. Okay.
Okay. Any question from others? Yeah,
I
have one question. Yeah, go on.
So I just wanted to ask: are you using concrete also in the 3D printing, or it's just the mortar only?
That is the mortar without the cost aggregate, but we always call it the concrete.
So you are trying to print with the aggregate as well, coarse aggregate as well.
Coarse aggregate, yes.
So what are the difficulties you face compared to mortar only and with coarse aggregate?
The most problem is we need the verify of the fine aggregate because we have a lot of problem when we pump it into the printing concrete, the printing machine. Sorry.
Yeah, why I brought this point is like we are also doing some basic things on spray mortar right now in AIT.
Sorry again, I cannot hear you.
Like why I brought this point here is we are also doing some basic kind of 3D printing in AIT using mortar. So the problem we are facing right now is if we are increasing kind of fine aggregates, with the spray mortar is giving us a big segregation, like segregation problem is happening.
Yes.
So do you face those kind of problem?
Yes, sure, we have, but we can solve it already. We have solved it already.
Okay, how can I know how did you solve it?
Same as Professor Piti is my team secret. Sorry.
You have to pay for that.
Thank you for the answer.
Yes, welcome.
Right, I can see that. Yeah, you can discuss later on in further by email or and so on. Right. Okay. Thank you very much, Dr. Thusawat. We can clap now.
Thank you very much.
And then move to next presentation, and by Mr. Satitam. Mr. Natapong Satitam is an assistant vice president at SSI PCL. He's also an advisor at the Iron and Steel Institute of Thailand, a steel structure subcommittee member under Engineering Institute of Thailand, and a committee member of steel application in construction sector under Southeast Asia Iron and Steel Institute. He has 5 years of international experience in building structural inspection, design analysis, project planning, project management, and project coordination. He has more than 10 years of domestic experience on infrastructure investigation, analysis, and evaluation, and has more than 10 years of technology and market and development in steel and construction. Please welcome Mr. Satitam. Mr. Satitam, the screen is yours.
Thank you, Ms. Chairman. Can you hear and see me okay?
Yes, you can see your screen. Yeah, thank you. Go ahead.
Right. First of all, I would like to thank Dr. Thanongsak for inviting me to join this very wonderful forum. And it's an honor for me to be a part of this very successful one. My name is Natapon, and today I would like to discuss about the innovation that our company has been doing just about a year so far. It's called PostConnect. Hold on a second. All right, here's the presentation outline that I'll be talking about today. I'm not sure anybody of you know my company, RIIE Steel Industry public company just yet. We're familiar with UK. We kind of invested in iron making facilities in Teesside about 6-7 years ago, I think. And yeah, we put a foot wrong over there, and yeah, then we come back and we kind of review our situation and kind of do some strategic review and move forward to the downstream and application. And about my company, we are located over the south part of Thailand in Bang Sapan district, Prachuap Khiri Khan. The facilities, there are a lot of facilities over there. The main facilities is the RIIE Steel Industry. RIIE produced the product called hot rolled coil on the right-hand side, produced from the very thick plate called slab. We imported from various iron making facilities around the world. And just want to show you our long-term strategy. That was initiated about 5-6 years ago. We would like to innovate premium value products from slab to hot rolled coil over the SSI facilities, and from hot rolled coil to cold rolled coil facilities over TCRSS, and then deliver to do some electrogalvanizing coating on top of the cold rolled coil over the facility called TCS. And we got the company called West Coast Engineering, WCE, to do the machinery maintenance for the steel producing facilities. Just a few years ago, SSI initiated some business unit called Building Technology to provide the steel construction service, mainly industrial building and warehouses. But this is one of the very interesting projects we did. It's a 3D freeform facade for the Wyndham Nai Han residence in Phuket. And just like I mentioned before, WCE, previously they did the maintenance work for all the steel producing facilities within the SSI group, but they kind of transformed their business into the fabrication and erection, and this is one of their masterpiece projects. It's very first steel highway arch bridge crossing the Nans River, located over the north of Thailand in Phitsanulok. The official name of this bridge is called Phra Ratchawangchan Bridge. And that project was delivered last year, just about time for the celebration of 2022 New Year. Well, so what about PostConnect? To understand the concept of PostConnect, I think it's better idea for me to show you guys about the base plate under the axial compression. Well, for the base plate and the column on top of the concrete, once we got axial compression from the upper floor transfer all the way down to the concrete foundation, and we cut the cross section, we're going to see the stress field of the concrete pier, just like on the left hand corner. Definitely it's not linear. It's going to be non-linear. And the way we do the design, we kind of simplify it into the linear distribution, just like this. For the construction process, the way we do the construction, definitely we gotta put the anchorage and install the concrete steel column on top, and do some adjustment with the leveling nuts. Once completed, just plug it in with the infill non-shrink grout. Once completed and the loads transfer, and the load will be transferred linearly according to the design code, and the design expression is just like this. We can conclude from this expression that, the affected area or disturbed area of the concrete will be about 4 times of the area of the base plate, or the affected area will be expanded just about twice of the width of the base plate. Looking closely to the base plate behavior, we gotta understand that once we have the base plate on top of the footing, once the load is applied, the concrete underside and underneath the base plate will have some kind of reverse pressure over the base plate, causing the bending of the base plate. And once the base plate got the bending, we can calculate the moment from the uniform load, and we can calculate the moment capacity of the base plate. Very simple. With all these concepts, we can come up with the thickness of the base plate in that bracket, in the red bracket. Okay, now we have the base plate, we have the column on top, we have the foundation. Let's take a look at this. If we revert it upside down, it's going to be just like this. And if we pour the concrete on top, it's going to be like this. With the through bolts, we can put the above column, upper column on top, and secure it with the nuts. And definitely it's going to be pretty much the same behavior as the concrete, as the steel columns on top of the concrete on the right hand side. And of course, we got to check that plane in blue, which is the concrete chair, punching chair capacity. But we are aware that on the right hand side, it's going to be very difficult to install, and no, it's not really good looking. We got to see a lot of cleats and bolts on top of the floor. So we think it's better to lower it down, place the upper column on top of the lower column, and just fill the concrete floor. So all the assembly will be hidden inside the concrete floor, which is really good looking in terms of aesthetic value. Architects would like it for sure. So with that, definitely the load from the column above will be transferred directly to the column below, and the floor load. Let's take a look at the plan of the floor. If assume we have the column arrangement just like this, and the column spacing is this. So the tributary area that we transfer on top of the column will be just about half of the column spacing on both sides, and so it's pretty much the column spacing. So this tributary area will be transferred load on top of the previously called base plate, but right now it's not a base plate, it's a cap plate. for the upper column, for the lower column. All right, the floor is pretty much supported by the cap plate. Again, this is pretty much the composite action between steel and concrete. So in order to identify the true behavior, I think we need to do some full-scale testing. This testing was conducted by Professor Ekachai from King Mongkut University of Technology at Thonburi over the AIT facilities. We did the testing last year, about the end of last year. For this presentation, I don't have the results just yet. It's on the way. I hope I come back next year, hope so, and be able to present the result, and hopefully we can do some pilot project this year. And this is a part of the plan that we come up for the assembly for the testing. All right, I'd just like to show you about some simple calculation for the thickness of the cap plate, assuming it's pretty much the same as the base plate design. So I bring this reference. It's a steel design guide number 1 by American Institute of Steel Construction. They show how to calculate the base plate, just like I previously showed you in the very first slide. Let's assume the base plate is produced from the high strength steel grade 370 megapascal. That's pretty high in Thailand, and the cap plate size is 60 by 60 centimeter. We would like to make it a little bit wider, just about the size of the concrete column, to avoid the problem of the punching shear. So we come up with the minimum thickness of the cap plate, about 1.5 to 2.3 centimeter thick, which is really reasonable in our consideration. So besides the minimum cap plate thickness, we would like to understand how much we could obtain from the concrete, the normal strength concrete, about 300 kilogram per square centimeter of the concrete. How much punching shear capacity we have. So we kind of do some simple calculation using that very familiar equation, and we can come up with this amount of the allowable punching shear to check with the service load on top. So I think we about on the right track. If we kind of need a little bit of shear reinforcement, we just put the headed stud inside the concrete floor. And I don't want to go into the detail of those calculations, and I kind of attach the reference with over here on this slide. So if you would like to go through the calculation, you can go through this website. We did some Facebook fan page called We Love Steel Construction. You can punch it in and see how it goes. So what's the post connect? It's kind of, it's a gravity column. It's made from hollow section with the state-of-the-art connection that not only enable load carrying capability and on-site constructability, but also maximize the architectural values because of the smaller columns and connection being hidden in the concrete floor. We got patent pending number over here shown, and we kind of file the patent aboard as well, and hopefully we could get the patent granted in years to come. Just like I said, the concrete column would make the floor, the space of the building a little bit not very elegant. With the steel column, it's much smaller. Let's say the concrete column would be about 50 by 50 centimeter. I can reduce down the column using steel to about 25 by 25 So the floor will be more elegant, the space will be maximized, and definitely the interior designer will like it for sure. With the way we do the assembly on site, I think it's kind of, you can see it here that we got the reason behind to do some testing to understand the real behavior. For example, if we have the tributary area, loading, dump all the load on top of the cap plate. Initially, we thought that the cap plate would carry all the loads by itself, but actually, I think there will be some forces from the floor slab to the brackets in the orange hatch, just like this, and some percent of the force will be carried by the cap plate itself, just like this. And also, we would like to understand the requirements for the top reinforcement, as well as the requirements for the welding and bolting. That's the reason why we come up with the series of the laboratory testing over the AAT facilities. We also prepare some design charts and tools for the designers who are not familiar with the design of steel columns and steel connections. This is a part table showing the different column size and different thickness, wall thickness of the steel, and different grades from normal grade SS 400 and the high strength grade HY 370 with different design philosophy from allowable stress design and to load and resistance factor design. It's very simple to calculate if you're familiar with steel design. First, you gotta identify the threshold, whether the column you're designing will fall into the long column or intermediate column behavior. Then you just follow the equation shown over here to determine the critical stress. Once you get the critical stress, you check again with the local buckling criteria whether the wall thickness is too thin, causing the local buckling. Unless otherwise, it will buckle under the flexural buckling using the compact section equation, just like this. It's very simple, but to make designers' life much easier, our team also prepare some mobile application. Everybody could download it for free via iOS or Android platform. It's just very simple. Once you download to your mobile application, you just punch in, select the component to be designed, select the shape, punch in the sectional and design parameters, and punch just one punch to calculate, and you get all the numbers, member strength, and you can also obtain the full report. But just make a little note that the full report is available for the upgraded version, just a few bucks only, because we just want to track who would like to learn a little bit more and who would like to get the full report in PDF format for submitting to the authority for construction permit request. That's all my presentation, and the last slide is the QR code for you guys if you're interested in the mobile application. Here you go. All right, if you have any questions, feel free. Thank you.
Thank you very much for your talk, Mr. Satitam. Any questions from the audience? Well, I have one question. I know you work for a steel company. And the scheme you presented here is like equivalent to flat slab construction, where concrete column and flat slabs.
All right.
But in particular, your design uses steel column. Hence, you need to have a cap plate to connect those two steel columns, and also you need to have some space for where slabs can sit on.
Yes, that's a team.
So why can't we just have concrete flat slab construction instead?
It's a very good question. Well, to be honest, we look around in terms of economical value. We look around in terms of the feasibility and the popularity of the construction in Thailand. We gotta accept that the building construction in Thailand for the floor slab, post-tension concrete is the most common, very popular. The reason behind, I think there are several reasons. The first reason is Thailand is not in the seismic prone area. So thinner floor will not affect very much with the structural system in terms of the diaphragm action. That's very important. We're not going to see a lot of post-tension floor in California, New Zealand, or any other parts of the world where affected by high seismic. Secondly, in Thailand, once we got a permit, there are height limitation. So the floor, the thinner the floor is, the many stories, the more stories you can fit in your building. So the developers would like to build the building just to fit in what's required according to the construction permit by adding as many floors as possible. So the post-tension floor is very common. And looking at the supply side, the post-tension floor is can be designed by various designers. There are a lot of design houses in Thailand. So, and besides all these factors, the awareness of the users, the building owners, they like that. They're okay with the post-tension floor. So looking at the numbers, the construction cost of the post-tension is very cheap. It's much cheaper than many other floor plate construction system. So I think the majority and will be the most popular system in Thailand for the floor plate will be post-tension flat slab.
So
looking
have
at
you used
column
your
itself,
scheme?
what's
Sorry
that?
to interrupt. So have you used this scheme in any building in Thailand already?
Oh no, not yet, not yet. Just like I
So you
said,
need to
it
persuade
just-
the client to
Right,
use this
right.
scheme.
Right. We would like just to plug in some part of the structural system, just the gravity column, just to be the smaller size of the column, so that the owner would get more elegant floor space, bigger floor space, because the column is much smaller and the installation is easier, and the design of the column could be done by a steel company. So we will be able to reduce the workload by the design house, who is the main designer of the building.
Right. Okay.
So,
thank you. Yeah.
Yeah. Right.
So any other questions from the audience?
Excuse me, I have a question.
Yeah, go on.
Can you hear me?
Yes, we can hear
yeah.
you.
Okay, I want to know, do you perform any analysis on the seismic performance of such connections?
Perform the analysis of what again? Sorry,
Seismic analysis.
Yes,
Oh.
yes. I want to know how do you anticipate the seismic or earthquake performance of such, connections in the future?
Just like I previously mentioned, this columns is mainly the gravity column. We assume that the columns, the lateral force will be taken care 100% by the lateral system, either shear wall system or base frame or moment frame system whatsoever. But the gravity load will be taken care by this. So let's say if it's in the high seismic zone, you got to design the lateral system accordingly to the requirements by the regulators you're building in. Yeah. So it doesn't fall into the case of the seismic design because it's designed to carry the gravity load only.
Okay, thank you for your answer.
Thank you.
Just quick advertisement. If anyone want the full report version, you got to pay about £2.
Very cheap.
Very cheap. Yeah. Thanks for giving
Very
free.
cheap. Yeah.
All right. I think it's about
Thank
time
you.
now.
All right. Thank you very
Thank
much.
you very much. Yeah, thank you very much, Mr. Satitam. Yeah, let's clap.
All right. Thank you very much.
And we have 2 more presentations, and it's now 7 in Thailand. So we hope to wrap up everything around 8:30 or before around 7:30 or before 8. So the next presentation will be modeling chloride diffusion in wetting and drying concrete. Presenter is Dr. Nattapong Damlong Viryanupap. Dr. Nattapong is currently an associate professor in Department of Civil Engineering, School of Engineering, University of Phayao, Thailand. His research interests focus on computational modeling of multi-physics transport in concrete, green concrete structure for sustainability, and reutilization of various solid waste in concrete structure. Please welcome Professor Nattapong.
Good evening here in Thailand and good afternoon there in UK. So today I'm gonna talk about my research topic on the modeling chloride diffusion in wetting and drying concrete. So first, let me share my screen. No. So everyone see my screen?
Yes, yes.
All right. So here is outline of my presentation today. I'm gonna talk about what is the problem caused by chloride ions, why reinforcement will corrode, and how to predict the reinforcement corrosion, and then I will talk about conclusions. So as everyone knows, chloride-induced corrosion of the reinforcing steel is one of the most severe problems for long-term durability of concrete structures. This can cause cracking, spalling, and delamination of concrete cover. So leading to the reduced load-bearing capacity and service life of structures. So if we have the prediction model, we can use this model to predict the chloride diffusion in concrete structure, and then we can schedule the maintenance and rehabilitation plan. So this is gonna be useful for engineers and I think like maintenance management. So the picture shows the corrosion of the reinforcement of the concrete structure due to chloride ions. This one also. So one of the major sources of the chloride ion is from de-icing salt. But in Thailand, we don't use the de-icing salt because there is no snow in our country. So we're gonna see the problems of the corrosion of chloride ions in the USA and in Scotland. So they use the de-icing salt for the snow melting. The 3 major components of the de-icers they commonly use is sodium chloride, calcium chloride, and magnesium chloride. But in our country, we can see this problem in marine structures. So these pictures were taken in Thailand. You can see the severe problem due to the corrosion of the reinforcement due to chloride ions. So in the mechanism of the chloride diffusion in concrete, there are two periods. The first one we call initial period. You can see from this picture, the initial, the initiation period take longer than the propagation period. So you can see the green line is take longer. When the chloride ion reach the critical value of the chloride concentration in the reinforcement, so it is gonna take corrosion very fast. You can see the red line. So here is how we can solve the problem of the chloride induced corrosion in concrete structures. So when the reinforcement will start to corrode, so this stage is in the threshold value of the chloride concentration. And when the chloride reach the threshold value in the surrounding environment, so this step, we can use the prediction model to determine the chloride concentration, and we can see how chloride penetrate, how deep the chloride ion penetrate into concrete structures. And another way is we can protect the reinforcement from the corrosion by using chloride removal techniques. One of the classical models we use to predict the chloride diffusion in concrete, showing here. This equation is derived from the Fick's law. This is very simple. We can use this equation I showing here. You just put the parameters in the equation. For example, CS is a chloride at the surface of the concrete structures, and D is a diffusion coefficient, and X is a depth of the concrete. Sorry, and T is a time. So we can calculate the chloride concentration at any depth at any time of the concrete structures. So here is a chloride profile, plotting between a chloride content and the depth of the concrete in several times. For example, 5, 10, 20, 35, 50, and 100 years. And also you can use this equation to predict the service life. You can see T here. You just put the chloride threshold value, chloride content at the surface, and the depth. Finally, we can determine the service life by obtain T from this equation. So that equation can use only in the fully saturated condition, but we can use the simple equation. We cannot use the simple equation in other surrounding environment. For example, in the wetting and drying condition, or that equation cannot use the effect of the migration due to electrical coupling. So if we want to consider the electrical coupling, we need to use another equation called Nernst-Planck equation. And also that equation cannot use by combining the chloride binding between liquid and solid phase of the concrete. And also the simple equation cannot be used for the chemical reaction between ionic species in concrete pore solution, such as the simple equation cannot consider for the electrical or chemical reaction between chloride and other ions in concrete pore solution, such as hydroxyl, sodium, and potassium. You can see from this picture, you can see this column, one part of the column immersed in the water. So this condition is fully saturated, right? And the top part of the column is over the water. So when the water level up and down, so this part of the concrete structure will be exposed to wetting and drying condition. So we need to use another equation to consider for the moisture effect. Okay, let's say in my model, I use the I call double porosity model. We consider pore in concrete structure into groups, a small and large pore, gel pore and capillary pores. And that's why we call this model as double porosity. And then we formulate the governing equation by using Fick's law. But we add another term. You can see the first term of the left and the right hand side is a mass balance equation of the Fick's law. We add the second term on the right hand side. We call like a mass exchange between two groups of pores. So when chloride ions diffuse in the large and the small pore, they will exchange together. You know, you can see here, they will exchange together. So that's why we added the second term in the equation. And also we need to have the moisture diffusion in our model, because we consider the moisture effect in our model. So that's why we need to have the moisture transport equation in our model. And then we modify the Fick's law equation by adding the mass exchange term and adding the chloride concentration and moisture dependent. You can see from this equation, if we don't modify the equation, we gonna have only chloride concentration. So we need to modify by adding the moisture dependent to the chloride concentration in small pore and in the large pore. And then we add the mass exchange of the large and small pore in our model. For the numerical examples, I used 3 cases of the concrete sample exposed to chloride concentration. You can see the surrounding surface of the concrete sample is sealed. So chloride and moisture cannot penetrate into this surface. But we let the top surface exposed to chloride concentration and the moisture. So in the first case, we run our model in fully saturated condition. So inside the concrete sample, we put the moisture condition equal to 1. So this means inside concrete sample is fully saturated, and then the moisture condition at the exposed surface equal to 1. So there is no moisture effect in this case. And we put the chloride concentration inside the concrete sample equal to 0. So this means there is no chloride content in the concrete sample for every case of our example. So the second case, we change the moisture condition at the exposed surface. I'm sorry, in the inside concrete specimen, the exposed surface moisture is still 1, is still equal to 1. The inside concrete sample we change to 0.15. So in this case, not only chloride gradient will penetrate from the top to the bottom surface, but also the moisture gradient penetrate from the top to the bottom surface too, because outside is more than inside. So both chloride and moisture gradient will diffuse from top to the bottom. And the last case, we change the moisture condition at the top surface. So we just put like wetting and drying cycles. You can see from this picture, from this, it's similar to a modified sine wave. You can see like it looks like sine wave. I just put the condition at the exposed surface, exposed to wetting and drying, wetting and drying, wetting and drying. Okay, let's see the result of the 3 cases. We can see the effect of the moisture in the second case and the third case. The first case is fully saturated. The second case is non-saturated, and the third case is wetting and drying condition at the exposed surface. From my study, I would like to conclude that we use a double porosity model to simulate the chloride diffusion in concrete exposed to wetting and drying condition, and the model is used to determine the chloride concentration profiles in the exposed surface. I mean, exposed to wetting and drying cycles. And you can see from the result, the moisture variation has a remarkable influence on the chloride distribution profile, particularly on the near surface, exposed to the, you can see here from the second case and the last case, this due to the moisture effect. So, all right, that's all my presentation. Thank you.
Thank you, Dr. Natapong. Are there any questions from the audience?
Yeah, I've got a question. It seems, really quick question. It seems that your model is analytical, which is the governing equation model involving many parameters and also boundary condition. How can you make sure that the prediction of the model is verified against any experimental data or something like that?
Yes, it's very good question. We need to validate our model with the test data. It is our future plan.
And I think if you don't have the test data at the moment, you can also try to compare the analytical solution with the numerical solution, which is like something like finite element, something like that. If the trend is go together, then you can use this information and the experimental works in the future.
Okay. Okay. All right. Thank you.
Okay. Thank you. So, shall we move to the last presentation by myself? Because now it's
please bear with us. Last but not least, Dr. Montian will show the last word.
The invention from Dr. Thanongsak I will show in my slide. So now 7:30. and I try to be short and quick, and we should have dinner or maybe lunch before 8. Okay, let me share my presentations.
Yes, let me introduce
okay, thank you.
To the audience. Yes, this is our final one, day 1. And Dr. Monsian Setkit is an assistant professor of civil engineering at Walailak University in Thailand. He received a PhD from the University of Michigan, and his research interests mainly focus on the behavior of reinforced concrete structures, recycled aggregate concrete, and fiber reinforced concrete. He is currently an associate dean of the School of Engineering and Technology at Walailak University. Okay, the floor is yours, Dr. Setkit.
Okay, thank you. Do you see my slide, my presentation?
No, we can't see it yet.
Not can see yet. Okay, there must be something wrong. Sorry. I think I already shared my slide.
No, not
Okay,
yet.
okay.
Nobody's
okay.
sharing screen yet.
Okay, let me try it again.
Yeah, something's coming.
Okay.
Yes, you can see your
thank you.
presentation. Thank you.
So it is the presentation about recycled aggregate, the concrete. And we discussed earlier with Professor Kim and Dr. Reyes about the application in structural application. So I think I will present my work in structural application of recycled aggregate concrete from research to engineering application at Walailak University. And our research team had 3 members, myself and Dr. Thanongsak Imchai and Dr. Sachapan Lilatanon. And it is the outline of my presentations. I divided the presentation into 4 parts. I will talk about motivation and research at Walailak University, and example of our past study and the current and future research in our groups. So in the first part, as you know, one of the main components of the concrete is the coarse aggregate, and the process of making the coarse aggregate cause some pollution and natural resource consumptions. And as shown in this figure, coarse aggregate is the largest main concrete component, constituting around 60% of the concrete volumes. And if you can make partial or whole replacement of natural coarse aggregate with the recycled one, we can reduce the utilization of natural resources, and we can reduce the concrete waste from constructions. And it is information in Thailand. The amount of construction waste keep increasing and becoming environmental problems. And unlike developed countries, where recycled aggregate concrete are actively studied and applied to real construction, Thailand had limited application of recycled aggregate concrete. So in this study, we select the better quality of the concrete waste. As you know, there are 2 types of the concrete waste. On the left side, it is construction and demolition waste, or CD and W. It contains the concrete, the mortar, the bricks, and low quality material. But in our research, we focus on the better quality of the concrete waste, because we have a lot of concrete cylinder left in our lab. And I think this is the good sort of the concrete waste. Its competitive strength is around 30 to 40 megapascal. So the challenging part is how we can crush this concrete, because in Thailand you cannot find recycled aggregate concrete in the market. So it's our job to make it happen. So let me tell you first, there are two confusing words that people maybe get confused between RCA and RAC. As you can see, RCA is recycled coarse aggregate. We call RCA it's aggregate that we use to mix the concrete and make the concrete, and we call the concrete RAC or recycled aggregate concrete. We start the projects a few years ago, maybe back in 2017. At that time, it's just small project for undergrad student, because we want to get rid of the concrete waste in our lab, and the progress of the project was very low because we did not have any machine to make RCA. And when Dr. Thanongsak joined us in maybe 2020, and last year we developed the crushing machine that make our life much easier. And we also start the application of RAC for structural purpose from 2019. And it is the early day from 2017 to 2019. As you can see, this lady, she is human labor. I mean, she worked hard, and it was time consuming to get the recycled aggregate. So last year we come up with the idea of developing a concrete cutting machine by getting an idea from the ice cutting machine. We also got some funding from the university, and this is the sketch of our conceptual design. The machine must be portable and can make the coarse aggregate from the size of 9 mm to 25 mm. And the machine is licensed to the university. It's powered by electricity, low cost and portable. So let me show you how it works with this machine. Okay, sorry. And basically, the percentage of RCA in common practice is about 20% or 25% in some countries. As Professor Kim said, in UK, it's limited to 20%. Using 100% of RCA is still questionable, and results from structural tests from many research work are sometimes contradictory. So our research team decided to fill this gap by conducting research on shear strength of RAC beam. And this is the common property of the coarse aggregate. NCA is natural coarse aggregate and RCA is recycled coarse aggregate. As you expect, the unit weight of NCA is higher than that of RCA. However, the water absorption of RCA is much higher than NCA. So we must be very careful when mixing recycled aggregate concrete. Otherwise, you're going to have the problem of workability. And this video shows the recycled aggregate concrete after mixing in our lab. And the third part will show you some past study in our lab for structural applications. We have several tests. Actually, we test slab, we test beam. And the first one that I want to show you is the shear strength of recycled aggregate concrete beams. There are limited research on the shear strength of recycled aggregate concrete beam. and the results are still contradictory. And if you want, the code maker to accept, to acknowledge, the use of RAC, I think we still need more tests so that they can be sure that it can still, apply to the real construction. But I want to mention that this is only a short-term performance. We still need to test some long-term performance also. But for our test, it's just a simple test. We have main parameters. They are percentage of RCA and the amount of longitudinal reinforcement, because we know that both of them can affect the shear strength of the beam. And this is an example of shear failure of our RAC beam with 25% of critical cost aggregate. And as you can see, it's just similar to the one with the normal concrete. And this picture shows the shear failure of the all test beam. They are quite similar. We have just natural concrete, 25%, 50%, 75%, and 100%. And the crack angle are quite similar. It's between 30 to 40. And we also compare the shear strength from the test to the shear equation of ACI, because we want to know how conservative is of our test. So we compare the test result with the ACI 14 edition and 19 edition. For 14 edition, it's still, the legacy equation, because we have used this equation for a long time. In Thailand, we also still use these equations to predict the shear strength of the concrete beams. But ACI 19 edition or the current edition, they offer a new equations to include the effect of longitudinal reinforcement, low W here, and also include the side effects from the depth of the beam in terms of lambda S. And this is the comparison between the old ACI code and the new ACI code. And you can see if you use the lower longitudinal reinforcement, maybe around 1%, the new ACI equation is more conservative. And we compare the shear strength of our test to the prediction by ACI, the old one and the new one. And you can see the shear strength of our test is much higher than the prediction of the shear equation from ACI. It indicates that we can still use the RAC beam without any shear problems. We also compile the shear database of 128 RAC beam found in literature and calculate the shear strength ratio and compare with the test from the test and the ACI. And we also found some unconservative result here. It below 1, it means unconservative, because this one is the shear strength ratio between the test and the prediction of the current ACI code. So we compare with the replacement ratio of RCA, and you can see most conservative result are from the 100% of RCA. So we decide to propose some change in the current ACI equations. As you can see, we propose the beta R to account for the effect of recycled aggregate concrete. And if you use 100% of recycled aggregate in your mix, we suggest you use 0.05, 0.75 in these equations to make sure that your beam are safe. That's the work that we have published, and we make some suggestions. And we also study continue our study on the recycled aggregate concrete. Now, our team are working on the combination of recycled aggregate concrete and fiber reinforced concrete. We use steel hook fiber with one hook end and double hook end. We call 3D and 4D steel fiber. We can make the concrete from 100% of RAC with strength more than 40 megapascal without any problems. And we also test the beam. And as you can see, we test the beam without shear reinforcement on the left side to see the contribution of RCA and steel fiber for the shear strength of the beam. And this is an example of the test result. And you can see we can prevent the shear failure using steel fiber and recycled aggregate concrete. And I have, some picture to show the failure pattern of the beam. Actually, I test 16 beam, but in this figure, I just show some of them. And you can see is you use just only recycled aggregate concrete without fiber or only fiber at 0.5% by volume fractions. You cannot prevent shear failure. But if you use at 0.75% or 1%, you can prevent shear failure and the beam will fail in flexural mode. That's and now we are working on the data analysis and some mathematical model for future publications on this project. We also did some tests on the punching shear of slab with recycled aggregate concrete. We done with the lab test, but we are still working on the data analysis. And for the future, we think we also planning to perform some tests on seismic behavior of structural component made from recycled aggregate concrete and some composite material to show the potential of recycled aggregate concrete in structural purpose. And that's all of my presentation. Thank you. If you have any questions, I'm happy to answer them.
Thank you very much, Dr. Satkit, for your presenting your experimental work. We now open for questions from audience. Any questions?
Maybe they are tired.
Your presentation must have been very good. Must have been very, very informative.
Yeah.
Reyes, any question?
Can I ask? Yeah, can I ask a question?
Yeah,
well, first of all, I have to say congratulations, because I remember the first time I went to see you. You had your students smashing concrete by hand. So I'm happy to see that there is a machine now that is helping you to get the crushed concrete.
Yeah.
I think my main I don't know if it's a question or a comment rather. Again, thinking of the intake of the solutions in the market, how is Thailand looking? Because I mean, there seems to be a lot of research going on, but in terms of actual applications, what is happening in Thailand? What are the opportunities? I mean, Professor Kim is also working on something along the lines, but how is the situation at the moment? Are the contractors and designers open to take in these solutions, or are they a bit reluctant, like in many other places around the world?
Yeah, I don't think so. I don't think it's gonna happen soon, because we rely on ACI code. As long as ACI code doesn't adopt any change in the use of RAC, it's quite difficult to push the structural application in the real construction. But I also talked to some the owner of the precast factory in our province. They also comment because they have concrete left over, a lot of concrete left in their plant every day, and they also want to take some advantage of this concrete waste. So that's why we try to push this one into the real construction. But I think it still need time. But what we can convince is about, maybe we use it just a little bit, maybe just 20%, just like the UK, because it's proven, right, that it works. I mean, if 20%, but for the 100%, I think we still need time.
Yes, of course. And I think when it moves to very high percentages, another concern would be the long-term durability as well.
Yeah.
Because obviously you showed already that the properties are quite different. So obviously that would need to be looked into in the longer term, because I think much of the reluctance from contractors and builders in general is liability. Because if something goes wrong, who's going to pay?
Yeah.
The one who builds the structure, yeah. So or the one who's liable for the structure. So for us, it's easy to produce new concretes, but then eventually, if for any reason something goes wrong, it's actually them paying the price, and that's why they are always a bit reluctant. So that somehow we need to find ways, probably through small demonstration projects, that the solution actually works also in the long term. But anyway, that's something we can discuss later on offline.
Yeah, Dr. Garcia's comment is very, very important. And I have, in line with that question, I have one question for you, Dr. Satkit. Yes, doing experimental work in a lab, that's the one thing. Yeah, but how about the design code? And you use some ACI code, but how about Thailand code? Does it actually specify how much you can use, or are you allowed to use recycled aggregate?
I'm not sure. There are the old code. I'm not sure. I think it allow only maybe 10%, if I'm not wrong. Yeah, they allow some, but very small amount of RCA. Yeah,
if it's allowed to very small, how do you get involved in Thailand code? Is there any way you guys can get into that committee and then try to have some lobby or campaign? So that will really help, because one problem in the UK, and companies want to use it, but they don't want to. Yeah, company, even though they want to use it, they said, sorry, the regulation cost does not allow, full stop. You can't go any further.
Yeah, that's the same problem here. And
so
we also rely on
to get into that area.
Yeah, and in Thailand we also rely on ACI code, and it's very old. 20 or 30 years ago that we use, the ACI, and it's very difficult to change, and that's the one thing.
Okay, so any other questions from the audience?
So in Thailand, we are trying to put Montian in the social media, so that the people from the government notice that, okay, let's put it in the policy, in the construction, or even, okay, if you use the recycled material in the construction, then you can, I know, get some tax refund or something like that. Then, people start to aware of using this. On Boxon, can you put Montian in the RCA working group as well? You said you have working groups. Yeah, he's really active person,
Yeah. I think
he bought a lot of hammer for students, even himself, and knocked the concrete by himself.
Yeah.
Before
Yeah, campaign and educating youngsters, educating the politicians and the lobbying politicians, all it'll work. Not only just one thing, for many different sides, that it'll work.
Yeah. Okay, I think it's about the time, and thanks for all you guys. And tomorrow, something more on about the seismics, composite, FRP, and numericals and winds, things like that. I think it's about the time, and everybody getting hungry here. It's about late now. What time now in UK?
Same here. 10 to 1.
Ah, right. Okay, you won't be hungry.
I am hungry.
Ah,
you know me. You know me already. So
actually, this project is support. Invite you guys from UK to visit Thailand. Probably see the installation first, the end of this year. Both of you can come and visit us as a visiting professor, and let's see how it's going. Okay, this opportunity, I thank all of you, and hopefully to see most of you tomorrow. Thank you.
Okay. Thank you. See you tomorrow.
Thank you to all.
Thank you. Bye.
Have a nice
Bye.
evening.
Bye.
Have a nice afternoon.
Bye.
Those in the UK.
Bye.
For now.
Bye.
Bye bye.